Press it. Then speak.
Okay.
Okay.
Good morning, everyone, and welcome to the final day of the Qiskit Fall Fest. It has been a wonderful week of learning, discussions, and interaction with the quantum community, and we are delighted to have you with us as we conclude this series today. Thank you all for your participation and for your engagement throughout the event. As we begin, let us extend a warm welcome to our speakers for the day and look forward to another insightful set of sessions. For the first talk, we have Professor Sanjit Chatterjeee, who is going to give a talk on cryptography in anticipation of quantum computer. In this talk, he'll provide a general introduction to the field of post-quantum cryptography and how widely used public key cryptographic schemes used in practice to secure communications are known to be completely breakable by quantum computers. Dr. Sanjit Chatterjee is a faculty member in the Department of Computer Science and Automation, Indian Institute of Science, Bangalore. His current research interest lies in the design and analysis of quantum-safe public key crypto systems within the paradigm of practice-oriented provable security. We now welcome Professor Sanjit Chatterjee to begin the session.
This is the micro, you don't have. Okay, so thank you. And so what Vivekananda said is that particularly for the youth, it's much better to play football than reading Gita. Okay, so today it's a gorgeous day, so I think most of other participants, they're enjoying the weather outside rather than coming for a boring talk. So you can also take that advice from Vivekananda and interpret in the current context and then leave this auditorium, then everybody will be happy, right? But looks like somebody, at least some of you don't want to leave, maybe you are too lazy. So we'll have some fun today. So when I included this one here, the purpose was slightly different, but then when I was waiting for the delegates to come, I thought that this is probably the perfect one. I am waiting for Godot, so to say. So I'll not explain that existential drama to you. You can all look at now. Chatterjeee tells us everything. Chatterjeee is our best expert and friend, so you can look at if you want. So today I am going to talk about something not directly related to quantum computer, rather than what we are doing in anticipation of quantum computer. Okay? So if you see that there is a lot of quantum computing in these sessions, then this is a kind of exception. Not much quantum computing will come in the foreground. It's something that is in the background. Okay, so crypto basically has two complementary aspects. One part is to build crypto systems, and then it provides essentially foundation for our digital communications. So all you are, even now probably many of you are looking at your screens. So digital communication, this is what provides you the foundation of security, and then the primary goals are to achieve what is called confidentiality, which intuitively we all know. And another aspect is to achieve authenticity of the data that you are receiving. Okay? So So there is then the other aspect. So if there are good guys who are trying to achieve all these goals, then there will be, so to say, the bad guys who will try to break those systems. That's how the game goes, right? And it so happened that this particularly cryptanalysis, it played a very important role in the development of both computer science and also the related technology. How? So, since you are here, I thought I will ask you some quiz questions. So, let me start with an easy one. So, can you identify this one? Sorry? Quantum hardware. Anybody else? What is this? Yes, you are, of course, right, but can you make it some more specific? Anybody else? So what is this? Any idea? Or so the backbenchers, you are sleeping there? Have you seen this image before or not? I am asking the backbenchers. How many of you, how many of you seen this, can identify this? Then you can tell, right? Sorry? It's a cooling system you are saying. Okay. So this is essentially the dilution refrigerator. Inside you can say that way this so-called quantum computer is there. The qubits are there, if at all. But what is this? Sorry? Okay. Anybody else? Any guess? So she is making a guess. Sorry? Fast? Okay. Anyone? Any guess? Sorry? Punching machine. So, this is the world's first digital computer. Its name is Colossus. So, these ladies, they are operators. They are operating the machine. It involved vacuum tubes and other aspects. So, why was this digital computer built? So, what was the specific purpose? Any idea? Complex mathematical problem. What type of problem? Any idea? Laser. Accounting. Factoring. Okay. So this first digital computer was built for a particular cryptanalytic purpose, to break a particular crypto system. And that crypto system was used by Hitler to communicate with his generals. Who worked on this? You have any idea? Alan Turing didn't work on this particular system. Alan Turing worked on a different system. That's what you have learned, Enigma. And that was not the encryption system used by Hitler. That was used by the German military for its more day-to-day communication. Hitler used a different encryption system, and that was broken by another mathematician. His name is William or Bill Tutt. He later became a famous graph theorist. At that time, he was a student like you, but a PhD student at Cambridge. He was working on this problem, and then he figured out a way to break the crypto system, but that required a lot of computation which required developing a faster computing machine, and for that purpose this machine was built, whose name is Colossus. These people, they are the operators of that machine. Okay. The point I am trying to make is this type of what I mentioned in the previous lecture, whether you look at this first digital computer or today's race to build much stronger quantum computer, there is and this is not just the beginning or end of the story. There were other incidences even before this first digital computer was built, that many of the techniques that you use now routinely have been used for breaking crypto systems. That itself is a fascinating history which I am not going to, of course, go into, but if you wish you can always look at that. Okay. Now tell me, what type of crypto you have used today? I am asking today, have you used any crypto? So what encryption have you used today? Okay, anything else comes to somebody's mind? Maybe the younger generation, you are more hooked to your smart assistant. So you tell me something. Have you used any type of crypto today? Why doing UPI payment? Anything else? Have you used? Sorry? Okay. So somebody said WhatsApp, somebody said UPI, anything else comes to mind? So for example, right now are you connected to the IISc Wi-Fi? Yes? Does it involve any crypto? Suppose right now probably your favorite app is getting any software upgrade. Does it use any crypto? UPI somebody said, WhatsApp somebody said. Say you are connecting to your mobile service provider. Why should the mobile service provider allow you to connect? If you try to connect to a different mobile service provider, will it allow you to connect? So how do they distinguish between who is a legitimate user and who is not? Have you thought about these questions? Do you think this is a valid point? So if you try to connect to a different service provider and if you are able to connect, then how will they make their money? How will they make their profit? Right? The Wi-Fi, anybody comes here and will be able to connect? So now I am just giving you some lists that, okay, so you can think whenever you are using some form of digital communication, is there an element of crypto involved there or not? Or so can you find any application when you are communicating digitally? Can you find any application where crypto is not involved? So you can do that exercise to find out if there is any applications. So do you know that Bluetooth uses? So some of you are probably connecting your smartphone with your Bluetooth, right? So does it use any crypto? You said yes. Sorry? Key will be generated for pairing. Very good. So you know activities that we do these days as we get more and more digital, we have to depend upon crypto, which provides, so to say, the foundation of our trust in the digital world. Without crypto, all these things will simply collapse. Okay. So let's look at what kind of crypto we use. So for example, when you are getting your software update, I said that you need authenticity. You don't need confidentiality. Why? Why you just need authenticity and not confidentiality? You already attended my lecture 2 days back, so you can't respond. You are not allowed. I'll ask questions later for you. So you all have your software app, right? And you get updates. You may not even know that you are getting updates. So what is that update basically? Sorry? It is? So some software code, right? Let's say sent by Google or some other app provider, whoever it is. So my point is that it's extremely crucial that the software is authentic. But do you really care about our confidentiality? Why not? Right, as simple as that. So just think in simple terms, right? So when you are getting an update from Google, probably 1 billion users are getting the same update, right? So confidentiality is not an issue there. What is issue is authenticity, and the cryptographic mechanism that we use. There is a lot of crypto involved, but the primary tool that we use is called digital signature. So digital signature is something like your signature, just like when you sign on a check that provides the authenticity that yes, you generated it. Similarly, digital signature is providing a digital authenticity stamp on your whatever message you have. Okay, so think it simply in that term. Okay, so how is such things done? So the primary tool that we use for generating digital signature, this is not the only one, but the primary one that is used is something called an RSA signature. Have you heard of RSA? How many of you have heard of RSA? So do you know what RSA is? Some of you may know. So again, it's not very important to go into those details. I have just kept it here. The main point is that you will choose 2 prime numbers. I hope you all know what a prime is. Then you will compute something called the product of these 2 primes, and then you have to do quite a bit of other computations. Then primarily this product of the 2 primes along with this number called E becomes your public information, so which is known to everybody else in the world, whereas this information D becomes your secret key. Okay. So if you consider, say, Google is sending you some software update. Okay. In that case, this is Google's public information which all of us have, and this is something that is Google's secret information which nobody knows. Okay. The details may not be very important for you if you don't know. Then if Google wants to prepare that signature, what it will do? It will do this computation. There is something called a cryptographic hash function which works like a magic, which generates, you give no matter how large a message it will always generate a fixed length output. The output, if it does not matter whether it is a megabit, gigabit or petabit, it will generate always, let's say, some 512 or 256 bit output. And this is the output which matters. On that output, Google will use its secret key to generate its signature. Okay? And that signature, which we call sigma, is sent along with the software code which you have, or your, say, smartphone has right now, let's say, downloaded. Then what will you do? You means your smartphone, what it is doing next, it will first check whether the signature verifies the validity of the signature, and to check the validity of the signature, it will do a computation here which involves this E, which is part of the public key, and N, which is the product of two primes and part of the public key. Okay? At a high level, this is what is happening without you noticing anything. So there are many issues involved. First of all, it has to be done very efficiently. Otherwise, if your software update validation checking will take 3 days time, then you will not be able to use it. So everything has to be very efficient, but at the same time, it must also be extremely secure. Now imagine that somebody else, a third party, an adversary, is able to produce a signature on behalf of Google. Then what kind of issues you will face? Imagine. Yes. Just say something. Suppose somebody else is able to produce a signature on behalf of Google. Then what it can do? No, it will not be as such access your system, but it will be able to implant a malicious code in your system. Then that can be used to access and what not, right? You see the point? That why it is very important that what you are downloading is authentic, and that authenticity is provided by what? IC signature. And this is all the devices that we are using is essentially doing. Now the question is that how can the adversary or this malicious party produce such a forged signature? So, one thing is that if the adversary has its code, let's say, then it can solve this equation. If it can solve this equation, then what will it gain? What will it get? The S, it will solve for S. So, I have my M, N is known, E is known, if I can solve this equation. Any idea how this equation can be solved? Have you seen such equations in your life? So, how difficult is solving that equation? So, if there is no mod n, will it be difficult? Mod n, you know what is mod n? So, you take the remainder essentially. How difficult is this problem if there is no mod n? Sorry? It's not difficult, but it must be difficult in this setting. So what it can do, otherwise it can also try to factorize n. So if it can factorize, then you can just go back and check that it can easily produce a forgery, right? That you can check. Okay, so then the task for the adversary is to solve, let's say, these problems, one of them. And this brings us to the question that really how difficult is factorization? You must have done some factorization in your school days, right? How did you do your factorization? Do you recall? Have you done some factorization in your life? Maybe you forgot. How difficult? How difficult is multiplication? Sorry? Easy. How easy? Anyway, so but you are saying factorization is difficult, but then how did you actually factorize? If you are given something to factorize, how did you factorize, you remember? How did you do that? LCM, okay. Some method you use. So how, if the numbers become larger and larger, how difficult it will be? You can think about that. So when this RSA was first introduced, then there is this popular magazine called Scientific American, which is even published today. There was this person who used to write a popular column, and there he introduced this RSA, and there he mentioned that it is a new kind of system which will take millions of years to break. And then this RSA, which was developed by these 3 MIT professors, they also provided a small challenge for the Scientific American readers, which was encrypted using a 426-bit RSA key. 426-bit RSA key, by that I mean this N is 426-bit. N is a product of 2 primes. Then each prime will be how long? Roughly? If the product is 426-bit, any idea how long each prime will be? So half of that bits, so say 200, around 210, 20 bits. Then if you multiply 2 numbers of that bit length, you will get the answer as this 426 bit. It's easy. Even if you do it decimal numbers, if you multiply 2 decimal digits of say 2 digits long, then what is the product you expect? The logic is not any different when you go to binary, right? And they gave a token price that, okay, if you can find out what is encrypted, you will get $100. Just to generate some curiosity. Let's see how difficult this problem is. Any idea how long it took to break it? Or is it strict, unbroken? So it took 17 years by a Dutch group to break that challenge, and this was the plaintext they figured out. Of course, they spent much more than $100, several order of magnitude more, but as a symbolic gesture, they donated this money to an organization called Electronic Frontier Foundation, which works primarily on digital rights, digital privacy, etc. Okay. Then there are a series of RSA challenges. The latest one that was broken is 5 years ago. It's called the RSA 250, which roughly corresponds to 829 bits That means the primes were around 400 bits. Okay? The previous record was broken a year before, not even a year before, that was RSA 240, but the previous one was broken 10 years before. So, and then there are many more such RSA challenges which remain unbroken. So when Google is sending you that software update, how long do you think its public key is? How many bits it uses in the public key? It can't definitely use 829 bits because that is already factored. So how many bits, any idea? How many bits are used? Or let's say when you are talking to your bank, you are doing mobile banking, somebody mentioned UPI. So how large is their RSA public? You have any idea? Any guess? They are supposed to be at least 2048 bits. Better if you use 3072 bits. Okay, so this is where we are, the known factorization, and this is what is used. Okay, so you are probably safe. Then somebody mentioned pairing two devices. Again, I will not go into the details, just I will mention that what you use as Bluetooth, you all use this term, but what is Bluetooth? Bluetooth is actually, so to say, an industry standard to develop, you can say, the personal area network or body area network. So you are forming a network amongst the devices, let's say, you are using. At the very least, you are using probably your earphone and your smartphone. But of course, you can connect with your smartwatch, this, that, all these things, right? Your speaker, whatnot. Now, but this is going over a channel which is like the Wi-Fi, right? There is no wired connection. So it can still be possible for somebody to break into your communication. Suppose you are sending some instruction to your, let's say from your smartwatch you are going to make a payment, but somebody can come in and then make a different payment to a different person if they can intrude your instruction. So have you ever, when you used your pairing, have you ever asked that there is some numbers that you have to enter in the other device? Have you ever wondered what is that? Why you are supposed to do that? So this is, again I will not go into enter into the details. The main point is these two devices, they establish a key. And this is the key that they are establishing. There is an authentication part which is done manually by asking you that look at this screen. It has these numbers. You enter these numbers in the other device. So the two devices, they can authenticate that they are actually talking to each other and not to the adversary. That's the essential idea. Again, there must be some hard problem for the adversary to solve, and that hard problem is called the discrete logarithm problem. So you all know what is logarithm, right? You can compute logarithm. I hope you know that logarithm can be computed easily. Do you agree? So have you seen something called a log table? There earlier used to be something called a log table where you can look at the table and put these values. Now you may not need your smartphone will find that. But when you do it on the discrete domain, it can become very difficult. So that's the discrete logarithm problem. A similar thing is done when she was mentioning about WhatsApp communication. When you are communicating over WhatsApp, it's said to be end-to-end encrypted, and that also uses this kind of elliptic curve discrete logarithm problem. Okay. Now, the question is that when we try to have our system like, say, signature or encryption, then we want this should satisfy very strict security criteria. For example, I said that this RSA that you are used, the minimum bit length of the key should be 2048 bit, which means the primes will be of length how much? Primes will be of length how much? Sorry? 1024. So just try to imagine how large that number is. Okay. But often what happens that it's not that the cryptography is broken. People, when they are trying to attack the system, they will try to find the weakest link. So your system is as secure as its weakest link is. It's not that they always need to break the crypto. So it has a lots of details goes in when you try to build a secure system. This is a point we often forget, and this is where the attacks happen. So factorization, as far as we understand, that's why I mentioned about those challenges. So one primary purpose of those challenges is to figure out how difficult is this computational problem, say factorization or discrete logarithm. So it's very important for patent development happens through this, including in our technology. So the point is factorization or discrete logarithm computation is difficult as far as we understand, but that is true when we consider the conventional or classical Turing machine. That's the model of computation we are using. But it has already, and probably you all know, that when it comes to simulating things at the subatomic level, then these machines are hopelessly slow. And that's where came this idea that why not use the property of quantum mechanics to build quantum computer. And it's generally attributed to Feynman, but it's not just Feynman. This Russian mathematician Manin also independently proposed the same idea around the same time, because that's when people started to realize, okay, whether we can use these properties to our benefit. Okay, so again a small quiz, so you probably all know. Who said all these things? Can you mention? Figure out? Einstein, first one. The second one is also Einstein. So the point is quantum mechanics is extremely successful theory, but what goes on really inside is something that people still debate, and these are the people who worked on various aspects of what is called the quantum mechanics, but still they had issues. So finally what Niels Bohr said essentially is shut up and compute. That is a simplified way of saying what is called the Copenhagen interpretation of quantum mechanics, that okay, let us look at what we can do with it. Let's not ask what is happening internally, and that is very, very successful, even leading today to discuss about quantum computers. Good. And you all know probably these terms, so I need not go into details of them, right? So you have heard of all these terms, right? So these are essentially the properties that are used in one way or the other to realize something more than what we can do classically. Okay. Good. But the question was then, whether we can really use these quantum principles to build something that is useful. And one of the first works was by David Ghosh, who developed this idea of quantum Turing machine. So Turing machine is essentially a model of computing, and then he was able to develop this notion for quantum Turing machine, how will you use quantum mechanical principles to do the computation. And not only that, then he asked this question that fine, but is there any kind of computational problem where this is useful? And he gave a very simple example. He showed that I can distinguish between two functions, whether it is balanced or constant, but the function is from 1 bit to 1 bit. So what does that essentially mean? 1 bit to 1 bit, if you are given a function, you can't look at inside. So what is the constant function from 1 bit to 1 bit? What do I mean by a constant function from 1 bit to 1 bit? What is the constant function, first of all? So if you give input 0, output is, what is the output you get when you give the input 1? And if it is balanced, mean 0 can go to 1 and 1 can go to 0. Or 0 can go to 0, 1 can go to 1. Right? Agreed? So now if I ask you that you can't see inside and tell me whether the function that is given to you is constant or balanced. And you are allowed to query this function. So how many queries do you need to decide? How many times you have to query the function to decide whether it is constant or balanced? Can you do it in just one query? You query it, it will give you output as 0 or 1, but you don't know whether this is a constant or a balanced. So, which property he used to show that just one query will allow you to decide whether it is constant or balanced? If you know a little bit of quantum mechanics, which property do you think he used? Cat is both dead and alive in a superposition. Or Einstein asked famously that if I don't look at the moon, I don't know whether it exists or not. Okay? So this showed that essentially, because that was kind of the starting point that showed that we can do something more using a quantum computer that we cannot do using a classical computer. So that gives the more power, right? Then there was a series of works culminating with this famous result by Peter Shor, who gave a very efficient algorithm to factorize numbers in polynomial time. This was followed by this Indian origin mathematician Grover, who showed that if you are going to search in a database which is unsorted, then the complexity of that search is square root n of the size of the database. If you are trying to do it classically, what will be the complexity? You are not supposed to answer. So you have to search the whole database, right? So here you get what is called a quadratic improvement. So all these showed that yes, quantum computers are powerful in theory, right? So for example, there are lots of issues involved. I am not going into I am just mentioning in results. For example, this Grover search that requires memory, that circuit depth and so on and so forth. It's not so simple as the way I am saying, but it is showing that it is possible to get improvement, sometimes significantly, like what Peter showed, than what we can do classically. So then it really created the interest. So if that was 97, then you see, if we continue with our story, then the first quantum computer only on 2 qubits was done in Cambridge by these two people. So this guy Mosca, we will encounter him again. So he was at that time a PhD student there, and they built a 2 qubit quantum computer. Then this is kind of things started improving, 7 qubits, 14 qubits, 17. Then there was this quite some news about so-called quantum supremacy. This Google and IBM, they are fighting the so-called quantum race. Then the latest, largest one is slightly more than 1000 qubit that happened in 23. But apparently now people are trying to build smaller quantum computers, put them into network, and not going exactly in this direction of increasing the qubits. But that may also happen. So given all this, so what is the largest number that Shor's algorithm has factorized? Your guess? What is the largest number that Shor's algorithm has convincingly factorized? What do you think? Sorry? 2-digit number. How large? Means so this is what we have so far. So it can come to 4 bits, and what is recommended today for the RSA application is 3072 bits. And if it is the timeline, so what do we expect? So we may think that, okay, there is not much to be worried. But as I already told you, that all our digital communications, including all military communication, financial communication, and so on and so forth, they require cryptography. They use, if they are using the public key cryptography, they are using either of these two. They are using either this RSA-based system or the elliptic curve-based system, and both can be theoretically broken using Shor's algorithm. Okay. Then in 2013, you might have heard of this Snowden revelation that NSA is capturing large amount of data. Even they have these submarines going over the optical fiber cables that are laid on the bed of the Atlantic Ocean to capture those data. Okay? And those data they can store, and then probably when they have enough computational power, they can break. So they may not be interested what you did 50 years back, but they may be definitely interested what, let's say, another country is doing. Or for the financial organizations, they may want their data to stay confidential for a very long time. That's where the concern is that store now, decrypt later. This is, in short, what is called. So this Mosca, whom we encountered in the previous slide, he came up with a famous theorem. And like all famous theorem, like E equal to MC², it can be explained in a very simple way. What he basically says that is x plus y greater than z. Means what? X is your security shelf life. How long you want your data to be secure. So how long you want your data to be secure? You? Sorry? Very short amount, very good. So how many of you use DigiLocker? So does it have your confidential information? So you have something called Aadhaar. It becomes extremely difficult nowadays that to buy a bus ticket without Aadhaar, I heard. right? So train ticket already they have done. Maybe auto ride will also require Aadhaar authentication. But do you know when you enrolled for Aadhaar or you are doing authentication, you are sending your data? So how long do you think those data needs to be secure? Or the DigiLocker that you use, is that a very short period? It needs to be secure for your lifetime, right? Now think of these military secrets, the state secrets, the financial secrets. So then you will get a idea of security shelf life. Yes, there are instances where you may need your data to be secure for 5 minutes, but then there can be instances where you need your data to be secure for 100 years. So it depends upon the application, but you have to take the worst case. So that gives your security shelf life. Then there is something called the migration time. Migration time basically says how long it will take to change the system. So all these machines and some of these things may involve hardwares need to be upgraded. This may easily take, depending upon the situation, 5 to 10 years. So if you sum them up, and if a quantum computer which is able to factorize is built before that, then this is what is called the collapse time. Then pandemonium will break loose, right? So tomorrow if you hear that the RSA of 2048 bit is factored, then immediately the whole financial system will collapse along with many things else, right? Agreed? Okay. So it's extremely important to be prepared. And to be prepared, we need to find out what is the collapse time. For these people who have been working in the area, they have come up with different types of predictions. For example, in 2014, this researcher based at University of Waterloo Institute of Quantum Computing gave these estimates that to break RSA, you will need roughly 500 million physical qubits. What is that? Physical qubits and logical qubits, any idea? So you have been attending this summer or fall fest for some time. What is the physical qubit and what is the logical qubit? Have you heard this term at least? Yeah, so the qubits are extremely fragile due to the property of quantum mechanics, this decoherence. So you have to handle them very carefully. And that's why all this gold used in this dilution refrigerator that we have seen at the very beginning to keep them happy, right? And he was giving an estimate that few thousand logical qubits, for that you need roughly 500 million physical qubits, okay? The nuclear power plant is required, obviously, then you imagine the refrigerator you have to build and the power it will consume. Of course, there is the other things. Mike Mosca, he 10 years back said that, okay, this is roughly the chance of breaking RSA by 2026, 1 in 7, which is quite significant. Okay. Now there is a folk wisdom also, because I am around for some time, so this is the folk wisdom we hear sometimes, that this is always 10 years away. So we don't really, so in 2005 it was 10 years away, 2015 it was 10 years away, 2025 also it is 10 years away. So we don't need to be bothered that much maybe. Okay, what happened in between? In 2019, these Google researchers came up with an estimate that From 500, they have made significant improvement. They said 20 million physical qubits is something that we should look for. One of them then in 6 years came down to a million qubits, which means there is a lot of activity happening. And a landmark result is actually, which is related to this result, is this reported by Google last year, where for this 105 qubit processor, they were able to achieve best error correction. So these are all physical qubit I am talking about. Like Navin is going to give you some glimpses of quantum error correction. So this is what essentially required to get this fault tolerant quantum computer. But roughly now the situation is that each logical qubit requires 1000 physical qubit. That's the best we have now. And if you want to go to this estimate of 1 million, then you need a 10,000 times increase, which is roughly 2 to the power of 13. So it's not that there is something like a Moore's law in the context of quantum computers, but this is kind of 13 doublings we will require to go there. But it is not expected that there will be any more significant improvement as far as algorithms are concerned, simply because if you are trying to factorize 2048-bit number, as I said, 1024-bit is the prime factors. So at least these many qubits, physical qubits, you will need to encode your numbers. So you cannot say that in 5 qubits I will be able to encode my 2048-bit number and so on. So you may not expect any significant improvements now onwards, because as I roughly mentioned that these many logical qubits will be required anyway. Okay? But there may be other breakthroughs. Nobody knows. There may be other breakthroughs, there may be alternative routes. And these are the information that are available in the public domain. We have absolutely no idea what is happening in the government agencies. For example, the first digital computer that was built at the what is called the Government Communication Headquarters of the UK. Right? And they did not go and publish, like Google will claim that supremacy, that we have the best quantum computer. IBM will say that no, we achieved quantum supremacy. They will not do like that. They will do things completely in secret. In fact, what we know as RSA was discovered by the same GCHQ scientist at least 5 years before RSA was published. But they did not make that result public because all these are classified information. So we really don't know that what is going to happen. So we have to somehow try to figure out. So many people were surprised again 10 years back when NSA came up with this announcement, which basically says that we need to be prepared with new generation of algorithms for cryptography that are able to resist quantum attacks. It then generated lots of news, speculation. People were seriously considering whether NSA has already developed a quantum computer in its backyard or whether they are afraid that China is going to develop one. And that's the reason they are doing. Nobody again knows for sure. Maybe we will know after 100 years. But this is what then got things started. Now the question is that why not use the properties of quantum mechanics to build a crypto system which is unbreakable? So as I mentioned, that the motivation for quantum computer came from this problem of simulating quantum system. So turn a problem into a challenge and then try to get benefit from that. So why not do the same thing with respect to cryptography? And this is the idea which was actually around for a long time. In the 1960s, this guy who was then a research student at the Columbia University came up with this idea. But then he decided enough of all this nonsense. He was trying to do something related to, say, harvesting solar energy and other problems because of the energy crisis. And he also had in between a fight with his dad, who happened to be the chancellor of the university that we know as MIT. So they are all strong people, so they are all fighting amongst each other. Then he ultimately ended up working, as he said, that enough with technology. This is going to bring doom to us. So let me just work as a laborer. So he went back to Jerusalem and was working as a construction laborer. So he passed away in 2021. You may think a pretty crazy guy, so his young days. And this is probably when he was in his late 70s. Okay, so the idea was around, but then you have to come back to IISc. And in the year 1984, IISc was celebrating its platinum jubilee, that is the 75-year celebration. There were conferences, invited talks, all these things happening. So there in this conference, one of the conferences was presented a paper which was titled Quantum Cryptography, Public Key Distribution and Coin Tossing by these two guys, which essentially, so they are the people who are working with Wisner, they knew about his works, and then they developed into what is called QKD, or quantum key distribution, that everybody probably all of you have heard of. Okay, so it basically uses these two principles called the no cloning theorem, which essentially says that the adversary cannot copy an unknown quantum state. The other one is that if it tries to make a measurement, then that will destroy the information. So in that case, it will be caught. In the other case, the adversary gains no information. So in theory, this is perfect. In reality, well, so there is these three laws of security that Adi Swamir proposed, which work remarkably well. The first security law is absolute security. Absolutely secure systems do not exist. They didn't exist in the past and they won't exist in the future. So, again let us go back to NSA. So, there was quite some information. People are proposing that why not use QKD. So, there was again a series of works by German secret agency, by the British secret agency and others. Finally, NSA made its stand very clear. It said that essentially the QKD is not going to solve your problem. It's not a practical solution. It has several issues, and then that NSA announcement ends with saying that what is called the post-quantum cryptography is a more cost-effective and easily maintained solution than QKD, and this is what we should go with. Okay? Good. So how much time I have? I have? Okay, so fine. So what is then PQC? PQC is post-quantum. So you are working still in the classical domain. You want to use all these machines that you are using, but you are using not RSA or discrete log-based system. You use systems that can resist even attack by quantum computer. By the way, so there are many myths. I am just asking this question. So suppose a quantum computer is developed, do you expect that then all these computers will become obsolete? So after this Grover's algorithm, how many significant developments happened as far as quantum algorithms are concerned? So not really many, because quantum algorithms, they work in a very specific ways. So only there are specific problems that can be tackled by quantum algorithms. They have their use in a sense, but it's not that they will replace everything that you are using. But on the other hand, they will need a lot of what we are using. So your smartphone you will continue to use at least during your lifetime, right? Okay. So if you remember that NSA announcement came in 2015, right? Then 2016, the US standardization body, they announced in a conference called Post-Quantum Crypto that they will initiate a competition to standardize post-quantum cryptographic solutions. Now, it's at least now this guy has made it amply clear that what US does, everybody has to follow, right? Otherwise, what do you get? 100% tariff, and it can be increased periodically, and then there can be jet planes coming. Okay, so then naturally everybody will follow. So there was a global competition, and then in 2024, NIST published some post-quantum cryptographic standards. In particular, they came up with 3 standards. The first 2, they are called Kyber key encapsulation. You can think this as I said that your Bluetooth pairing, you are generating a shared key using elliptic curve. Here you are using something which is based on what is called lattice-based crypto. So that's what Kyber is trying to do. Then dilithium signature is supposed to replace, let's say, the RSA signature used in your when you are getting this update or when you are doing the mobile banking to get the authenticated message. Then there is something called a hash-based signature. There are several other which are in the process of being standardized. For example, something called a Hamming quasi-cyclic code or HQC for key encapsulation, Falcon for lattice-based signature. Then there are still more a few based on different kind of mathematical problems on ramp. That means some of them will be selected and standardized. So there will be several post-quantum solutions available for use. Okay? And similar efforts are ongoing by other standardization agencies. Okay? And in fact, now it's mandated that this, say, RSA that you are using or the discrete log-based system that you are using will be deprecated by 2030, and it will be banned from use in 2035. So in 10 years, all these that existing systems that you are using or is used in world over, they must be completely abandoned. So that's the recommendation, and then one must migrate to what is called PQC or post-quantum crypto. Okay? But to do post-quantum crypto, you will need some hard problems. Like factorization is at the core of the RSA signature you are using. Discrete logarithm is at the base of what you are using for, say, when you are doing your confidential communication through WhatsApp. So we need some problem which are difficult for quantum computers. So let's start from some problem like solving n equations in say n variable. How difficult? So linear equations. If I give you a bunch of linear equations, can you solve them or not? Yes or no? That you can say. Yes or no? Yes. So how do you solve the bunch of linear equations? But what is there a technique? So there are several variables you have, so you know that the Gaussian elimination you have heard of, right? Now let me in this context quickly ask, if these equations are not linear but quadratic, can you solve? So if I give you a quadratic equation, you probably solved something, you use certain technique, do you remember? But if I give you, say, in several variables and several equations which are quadratic equation, anything he is saying no, he is not able to recall. So think about this problem, that can you efficiently solve that problem? Because ultimately you will need something which is hard for the adversary, and hard means it must be computationally hard for the adversary, right? So you need some mathematical problem. So this equation is easy. Solving a quadratic equation is probably, at least looks like, not so easy. Now what about these equations? Now I have linear equations in some variables, n variables, m many equations, but I am not giving you the exact solution. I am giving the approximate value. Apparently there is some noise added. So will you be able to solve it? So if I add some noise, so then a small amount of noise is added in these equations. What is your gut feeling? What will you do? Okay, think about that. But it's not very obvious that whether the method that you use when you are given these exact equations, the way you are able to solve, whether that method will work or not, right? So this may be a candidate problem, but still one needs to build crypto system out of it. I will not go into those details. I will rather go into that why these things can be difficult, where the difficulty arises. I will just discuss a little bit about that. So you all know vector space, right? Everybody here. So how many of you know something called this lattice? How many of you have heard of lattice? So what it basically says is that informally you have regular repeating arrangement of points in real space. Do you see any lattice here? Any example of lattice in this room? Just look at the floor and look at these corner points. Imagine it's extended, 2-dimension. Agreed? So then this lattice, now we are talking in abstractly in n dimension. Okay? Then it is all vectors of this form where these ci's are integers. Okay? So these bi's, they form a basis for the lattice that I called as L. then the length is essentially what is called the Euclidean distance. This is just like what you have done in the vector space, if you recall, right? And we'll call the lattice as integer lattice if the basis has integer coordinates. Okay? A little bit about lattice. If you know vector space, it should not be very difficult. Right? So here is a simple example of a two-dimensional lattice. The basis vectors are -2, -2 and 4, 3. So I said that all vectors that can be expressed in this form with integer coefficients, they belong to this lattice. For example, if you look at this point 2, 0, then you can express this way. So it belongs to. 3, 0 is this point. It does not belong to, because this is the only way you can express it, right? So here then which points are in the lattice and which points are not in the lattice? In this, which points are in the lattice and which points are not in the lattice? It's a just pictorial representation. You should be immediately tell me. Sorry? Blue points are in the lattice and these gray points are not in the lattice. Now if I ask you to give a basis that covers all the points, can you quickly tell me a basis for that both blue and gray points? Sorry? So he is saying 1, 0, 0, 1. Is everybody agreeing on that? Right? Then this blue lattice will be a sub-lattice of that, same also with the gray lattice. So you know lattice. Oh, wonderful. Now, it so happens that the lattice need not have a unique basis. In fact, we can show that a lattice can have infinitely many bases. Okay? Now, some of these bases, they are actually quite nice. So they are nicer than the other bases. And by nice, I just informally mean that those bases, they are shorter and closer to being orthogonal to each other. Okay? You know what is orthogonal. And shorter, of course, you know. Now, why we are interested in those nice bases? Because a nice basis will typically give you more information about the underlying structure of the lattice vector. So, if you are able to work with such a nice basis, then you can solve certain computational problems which you may not be able to solve that efficiently when you are working with a basis which is so-called bad basis. So all these can be more formally argued, but what I am just trying to give you some informal idea of how to work on the lattice. For example, if we go back here, so what do you think about this basis? Is this a nice basis or a bad basis? Whatever I said, I gave you some criteria, right? So they are shorter and closer to being orthogonal to each other. So even just based on this criteria, what do you think? So he is saying it's not a nice basis. Okay. Now what about this basis? Do you agree that this basis is also going to generate the same lattice points? This is orthogonal. Same lattice generated, but this basis is definitely much nicer than the one that I showed you earlier. Right? This is in 2 dimension. Then 3 dimension you can probably try to imagine. Then 4, 5 you can keep on. That's the beauty of abstraction. That's the, when you do with math, then you go there. Now suppose I ask you to tell me, given some basis and a vector, whether that vector belongs to the lattice generated by this basis. Can you find it out? Very easy. In fact, I have just shown you how to do that. You have to solve the linear equation. Then you find out. If I ask you that, I give you two bases and ask that whether they generate the same lattice or not, can you find out? Just extend this for each of the elements in one basis, see whether that belongs to the other, both way. So these are computational problems on the lattice, but these problems are easy problems. So they obviously will not work. Now let us look at another problem. It's called the shortest vector problem. It asks you, you are given a basis, give me a non-zero lattice vector of shortest length. 0 obviously belongs to every lattice. It is the shortest, so no, that is a trivial one. We don't want you to solve the trivial problem. The non-trivial problem is give me a non-zero lattice vector of shortest length. Okay. Now, my point is that you are given the basis. Now, this choice of basis will strongly determine how difficult this problem is. Okay. For example, if you go back here, you can immediately tell me which is the shortest vector, right? But that's why I use this one. If I just showed this, and this is in 2 dimensions, so I have all blue everything. Now imagine something is happening, let's say in 1000 dimensions. You can't even imagine, but just reflect on that, that suppose I am doing something in 1000 dimensions, even if I had not clearly identified the blue and gray, and if I have given just to these numbers, no image, and just told you, given this, find and give me a shortest vector, then you would be able to do that, but it would take some time. Whereas if I told you that here you give me the, you will immediately say 0 and given, so I know what the shortest vector is. Right? So that's the intuition behind what I am claiming. Then we ask this problem, okay, forget about exactly giving the shortest vector. Can you give me something which is approximately short, which is within a factor, say gamma. Gamma may be a value which is, say, greater than 1, say 2 times the shortest vector. So then it will be called approximate SVP or SVP gamma, where gamma is the factor by which it can go beyond the shortest vector. Okay? So is the problem clear? Good. Now there is in fact a very efficient algorithm which is attributed to Gauss, but which was known and in fact probably first figured out by Lagrange, that solves this problem when you are in 2 dimensions. Because those days people are mainly bothered about 2 dimensions, at most 3 dimensions. Nobody thought that 1000 dimensions will be of any use. Okay? But this problem starts becoming difficult as this dimension increases. And it is proven that this belongs to the class of problem. You need not know technically what is NP hard, but this is, you can think of the hardest problem to tackle. So this is a problem which is belonging to this class of NP hard problem. The fastest way to solve it takes time that is exponential in the lattice dimension. So if your lattice dimension is 100, then it will take roughly say 2 to the 100. You increase dimension by 1, then it becomes 2 to the power of 101. So that way it keeps doubling, right, just by increasing the dimension by 1. This way it will increase. Okay. Now the fastest quantum algorithm is still exponential. Okay. So this can be the basis on which we can build crypto systems that will resist quantum attack. So people first try to build crypto systems directly from lattice. Again, the story is, of course, you try something, then somebody will break and continue. Finally, the realization is that using the lattice directly may not give us something which is very efficient and at the same time quite secure. So then they went back to essentially what I showed here. So solving this problem is called learning with error. So there is error, but still can you learn the secret? That's the idea, learning with error. So this problem, if you apparently look at, has no connection with the lattice that I showed. At least the connection is not obvious. There is a quite bit of mathematics and computer science involved to show that this Kyber and dilithium, which is based on this learning with error problem, if you can break those systems, that will amount to you solving this shortest vector problem, or rather, to put it the different way, the best way we know to solve that learning with error problem is ultimately solving a problem on the lattice. In fact, that way, many crypto systems people have tried to break using lattice, including factorization problem and discrete logarithm problem. But of course, that involves quite a bit of math. Okay, so what I have done is I have given you kind of a flavor that what kind of problems you can depend upon to build post-quantum crypto system. One is based on lattices, the other is similar type of thing, again adding noise, called based on decoding error correcting codes. If you don't know, don't bother. Similarly, what I asked you to solve these quadratic equations, that can also be used to build crypto systems. But then there are different trade-offs. Certain things can be done in one system but not necessarily in other mathematical systems. So that way lattice is quite popular because it can be used to build many different systems, including of course encryption and signature. So one reason of their popularity. But so how things stand today? So 2015 I said NSS announcement, followed by 2016 NIST announcement. So Google immediately started trying with lattice-based crypto systems in their Chrome browser. IBM also in a few years started using again this lattice-based system. In fact, this is the system which is called this Kyber and dilithium. That is the general structure for them. It made its cloud quantum safe. So as of today, so when you are using your internet, so it's going all over the world, but it has to go through some servers. So who controls the internet traffic? So a large company, so the biggest company that handles the internet traffic is Cloudflare. So it's again a very interesting story that how they manage all these billion keys, which you can look at Cloudflare Java lamp story in the YouTube to see that how they do some of these stuff. So, okay, there are things that have been deployed, but then there are lots of applications which will require adaptation to PQC. Some of these are in hardware, some of these are smaller devices, so on and so forth. So that will keep people busy for a long time to figure out how to use these systems. One reason is that all these post-quantum systems are like you have to come here and then only they will serve you lunch. So there is no free lunch. At least you have to listen to my boring talk to get the lunch. So there is nothing like a free lunch. So you are getting a post-quantum security, but all these systems are significantly more complicated like RSA. RSA I can explain you in one slide. Elliptic curve cryptography, not exactly in one slide. Lattice-based cryptography, no way, not even in a single lecture I can give you a flavor of what is lattice-based cryptography. Similarly, to implement it is also complicated, and they consume more computation, they consume more bandwidth, so no free lunch. Okay, so how to then use it in resource-constrained environment? How to use it in, say, cryptocurrencies? Just a few I have mentioned. There are many more. If you want, you can think about. There are, of course, many research challenges because all these will depend upon some hard problem. So RSA, people are still working on factorization, and that involves quite a bit of involved number theory. It involves quite a bit of algorithmic development, even development of dedicated processors. So all these things will also happen or going on as far as quantum is concerned, or sorry, post-quantum is concerned. You have to come up with many different new systems because as more and more we are becoming digital, we'll need many applications of cryptography because that's where the foundation of trust is. So developing such crypto systems is going to be a research challenge. Then there will be questions of instantiations. So hardware, software, small devices, side channel, different people are very smart. They can figure out many ways to attack your crypto systems, right? So they can use many things and something that you cannot even imagine that are done to break crypto systems. For example, when a cryptographic computation is going on in my laptop, there will be some sound generated. So your desktop always generates sound. That sound can be correlated with the computation that is happening because there are those capacitors involved which will store and release charge. And if there is a strong microphone which captures that sound, from that sound some information can be revealed about your secret key, and people have actually done that. Adi Shamir, who was credited with RSA, in fact works primarily on such cryptanalysis. The work that I mentioned right now, breaking your RSA key from the sound generated by desktop, is something that Shamir did some 15 years back. So people do a lot of things. Okay. So that's the end of it. So if you want to dive deeper, a very simple way to start is go to these video lectures which has many, so to say, let me see if I have it here. There are all these starting with the very basics and then going on more details. So you can certainly explore this. Here I have, this is the Cloudflare. If you go there, you will find out something they call that what amount of traffic is now post-quantum encrypted. So you have several options. What is the all traffic when it goes? It comes down. If you remove humans, then this is how much traffic is encrypted post-quantum. They use something called this one, which you may not follow what it exactly says. So the first part is elliptic curve cryptography. This is a particular elliptic curve and this part is what is called the Kyber, I said. This is MLKEM is its official name. Full form is Module Lattice Key Encapsulation Mechanism, and 768 stands for a particular security level. So this is the status. Then you can of course look at various browsers. So they keep on updating. So this is, you can see that today how things are happening, how things are, so this is today. So you can figure out what is going on, and so that's it.
So there's a question from the live stream. Rehan Khan is asking, does there exist any work in which quantum encryption has practically been achieved to a level that one could say it's post-quantum safe?
So by quantum encryption, I suppose he's talking about quantum key distribution. Quantum key distribution in theory provides security, kind of unconditional security, perfect security. But as I said that, I should use this one. But it is not when it comes to actual deployment. There are many issues involved there. Some of the issues are mentioned in the NSA note that I mentioned. So if you can just Google search on that, go there, and they have provided references where they mention that why these are the issues. So most of the commercial deployments of QKD, they have been broken some way or the other, and they are extremely inefficient. Not only that, there is a cryptography. So these are the practical issues involved. So yes. Sure. Please use the microphone.
There was a disclaimer at the end that security cannot be achieved at the fullest at any point in time. So if you are giving up in that way, then commercialization is against these, right? So commercialization by Google or IBMs, they are claiming that we are considering much security, and they are...
No, it's so the first law of security that you are referring to due to Adi Shamir, that says that it's perfect.
Yeah.
Absolutely secure systems do not exist. He does not mean that the secure system do not exist. Absolutely secure system. So reasonably secure systems exist. You can say that way.
So for the business point of view, Google and IBM or people like them are claiming that absolute security do exist, so do pay for me or come with me.
Then they are lying.
They are lying. So
if they say absolutely secure system, then so if they say that I have a reasonably secure system, they are perfectly fine.
So this also make us to think that open source systems, maybe like Ethereum or blockchains, which are driving us towards that. If that becomes the norm, then even for this current trend on quantum, there should be some open way of doing quantum, right? So what is that happening there in the open quantum systems?
These are more like policy questions, right? So I'm talking about more like the science and the technology part, but this is a more like, of course, open research is most welcome. Then, and cryptography particularly, people have seen, so there is again a long history. What happens initially, so take for example the NIST. I said that they ran a global competition to select the algorithms. But if you go back to the 70s, they developed something called DES. DES was developed by IBM again, but there was no global competition, and NSA actually played a critical role in the development of DES, and which then people said that unless there is enough open scrutiny of these systems, then there may be vulnerability which are not detected. So the general consensus that has developed is that cryptographic algorithms, they must be scrutinized by global experts to the extent possible. And this is more or less what is even NIST trying to follow these days. So after DS came AES. And that AES was again through the global competition, and the cipher that was chosen was actually developed by two Belgian cryptographers. Okay. So this is what, and the principle is security by obscurity should be avoided to the extent possible. So this is
So
the
considering the properties which are going to be in the crypto world, we have to start authenticating that also through government policies, which I think recently also they are saying.
So these are policy questions. The governments take some things. So earlier, even there was something that was very funny. So there was restrictions on crypto exports. So the companies, so if you use something called an RC4, you may see that even today some of the places uses something called RC4, which was developed in the 80s, and which had a key provision of 40 bits. 40 bits even in those days did not give any security. But then the US government had a restriction that if you are exporting crypto, then the key length must be within certain limit. So then you are completely being fooled. You are given a crypto solution where the key is only 40 bits, which gives absolutely zero security. So there are all these
That is doubtable. Yes.
policy issues are involved. So yes.
Thank you so much.
Good morning, sir. How is India participating in PQC standardization?
Sorry?
How is India
So
participating
India has this,
Yes.
I think, BIS or BSI they call. So through that they are part of the ISO, International Standardization Organization. So as I mentioned that ISO is also standardizing some of these PQC algorithms, and India is a participating member in the ISO. So that way India is participating as far as I know.
Okay, thank you, sir.
Good morning, sir.
Yes.
Sir, I have two questions. So,
Please.
the first one is like you said, the fastest algorithm for the shortest vector problem. That is like still exponential. So, in general, like when we look at designing a crypto system for and securing it against quantum attacks, are you looking at max square root n advantage, or like, are you worried about something else? Because when I was reading up, I saw that in symmetric key encryption, they're not worried about quantum attacks because you're getting an at-max square root n advantage. And the second question would be similar to that. Like, can't you, for any crypto system, can't you just take any NP-hard problem and then just say, because it's NP-hard, you can say that for the foreseen future quantum systems, like quantum systems may not be able to crack it.
Very good question. So again, there are many issues involved. So in crypto, I use this maxim, the devil lies in the details. So NP-hard also has a very curious history. So you might have heard of something called a knapsack problem. Have you heard of that? So this problem is NP-hard. So it was used by Martin Hellman, and I think Diffie was his student at that time. Yeah. So they built a crypto system, knapsack crypto system. And this was immediately within a couple of years broken by Adi Shamir. And also lattice was used to break such knapsack crypto systems. So NP-hard is not necessarily a guarantee that you can really build a crypto system which is also as secure as the NP-hard demands, first of all. The other thing is that even if you have an NP-hard problem, you still have to resolve the question of how can I build a crypto system which relies on that problem. That is the most challenging part. So SVP on the lattice is an NP-hard problem. But when people try to build crypto system solely in the lattice, they are not getting something which is going to be really that efficient. So then there is a lot of research happened. Then people are working on something that I showed you, this bunch of linear equations with some error. And from there to SVP connection is not easy. So it's a very complicated story. So because why they are working there? all the crypto systems that lattice based, they work in the mostly in the learning with error situation. Whereas the security that depend here, the connection is essentially has to do with efficiency and security. So there is this fine balance one needs to achieve. Okay. So coming back to your first question, so for symmetric key crypto, yeah, again the folk wisdom is that if you are doing things right, then Grover's algorithm is most what you can achieve. But then there are also lots of details because Grover may need some memory, parallelization, there are issues. So does not it immediately mean that the square root advantage will translate in reality? There are issues, but yes, so for symmetric key, that way there is no significant development, of course, beyond what generically one can achieve with Grover.
Good morning, sir. Sir, here.
Okay.
Sir, I have a question on like QKD. So like QKD mainly relies on entanglement and which like
Entanglement, superposition is the basic thing that they used when
Yeah.
they
and
built the
like
system.
its ability on like detecting eavesdropping, right? So when eavesdropping happens, the data collapses because it's measured. So like how can we prevent or minimize the data loss while still being able to detect eavesdropping?
You can't. That's why they said that it's a denial of service. So if you look at the NSA points I mentioned, it's so easy to just mount a denial of service attack.
Okay. Thank you.
You can't do much. You have to physically protect, which is difficult. I guess we have.
Thank you, Professor Chatterjee, for that wonderful talk and for sharing your expertise with us. We sincerely appreciate your time and would now like to offer a small token of appreciation on behalf of the organizing team. We'll now move on to the next talk, but before that, we'll have a 15 minutes tea break and come back right around 11:18. Yes.
Okay.
Should I carry it?
No, I have my backpack here, so that's. Or you can just keep it there.
Yes.
Okay, we'll try. Yeah. As of now, yeah.
We will now proceed to our next talk. It is our pleasure to welcome Professor Navin Kashyap, who will be speaking on Introduction to Quantum Error Correction. Professor Navin Kashyap is a faculty member in the Department of Electrical Communication Engineering at IISc Bangalore. Prior to joining IISc in 2011, he served as an associate professor in the Department of Mathematics and Statistics at Queen's University, Canada. He holds a PhD in electrical engineering systems and an MS in mathematics from the University of Michigan and a BTech in electrical engineering from IIT Bombay. Professor Kashyap currently serves on the editorial boards of the SIAM Journal on Discrete Mathematics and Cryptography and Communications and has previously served as an associate editor for coding theory for the IEEE Transactions on Information Theory. He is also a past recipient of the DST Swarna Jayanti Fellowship in Engineering Sciences. His research interests include coding for communication and storage, quantum error correcting codes, DNA-based data storage, information theoretic security, source coding, and discrete applied mathematics. Let's give a big round of applause for Navin, sir.
Yep. Let me just adjust this. Yeah, thanks, Debarti, and thanks for inviting me to give a lecture here. Keep it somewhere. Yeah, so it's it's a very nicely organized workshop. I know that the students have been putting in a lot of effort towards this. So I hope that the talks so far also have been of a good quality, and that you have gotten something out of this up to this point. So the aim of this talk is to give you at least a brief, an introduction to the idea of quantum error correction. So I'm given to understand that people here in this audience are coming from a variety of backgrounds, maybe maybe some of you without any knowledge whatsoever of quantum computing or quantum mechanics, quantum information science. So I'm going to try to give it, give an introduction that that is kind of broad-based, does not assume too much background besides basic mathematics like linear algebra. So that is so the only prerequisite that I kind of assume on your part is basic linear algebra and keeping an open mind to be able to absorb some new ideas here. Okay. So quickly, the background. So I'll start with the background and motivation, and then before getting into the idea of quantum error correction, we will discuss briefly, very briefly, classical error correction, how error correction actually works for bits, classical bits, not quantum bits. Because the quantum error correction is actually built heavily upon classical error correction techniques. Then we'll do some quantum error correction basics to show how it is actually possible to do error correction in a quantum computing system. And then, if time permitting, or depending on how much time we have, get into more advanced techniques, or this, what kind of codes or what kind of coding schemes or error correction schemes are actually used, in practice. Okay. So I'll start with this thing that so we are currently in what is called the NISQ era of quantum computing. That is, it is the noisy intermediate scale quantum technology, where we sort of current technologies of quantum computing, various realizations of a quantum system, quantum computing system. There are various such realizations, physical realizations available now. They support maybe up to a few hundred qubits, if you have IBM systems, for example, that you try to access through Qiskit or any other front-end software. The back-end can be the hardware could be quantum hardware. So you may get access to a few hundred qubits at best. And these qubits are also very noisy. Okay? They're kind of very fickle. They're not particularly reliable. Any gate operations that you carry on these qubits will also be noisy and unreliable. The number of qubits that we have available to us are already very few. Okay, there are a few hundreds. So to work with that many qubits, you can't really introduce any extra redundancy into the system to carry out error correction. You have to just work with the noise in the system itself. Overcome the noise by kind of modeling it or programming for it. Okay, so you have your whatever quantum computing algorithms that you may be using will have to be deployed with the knowledge of the fact that there is going to be noise. Okay, so everything is very noisy and faulty. And so you have to also take whatever results that you get with a pinch of salt. It is not necessarily always going to be accurate. But now, as you move along, I mean, as we go further, like, so with a few hundred noisy qubits, there's really not a whole lot of quantum computing that can be done. So we have seen all of this, everybody has been exposed to the news on how quantum computers are going to give us is the next big thing, and like how it will solve all the big problems in the world, and because like complex problems that are very complex for a classical computer to solve can be solved through quantum computers very quickly, or there are quick algorithms for it. Shor's algorithm specifically, the integer factorization algorithm, is always touted as an example of how this, sort of the quantum advantage. It's also said that since many of the current cryptographic primitives are based on these hard problems like integer factorization, which are hard for a classical computer, but not so hard for a quantum computer. So these cryptographic primitives are no longer, will no longer provide the same level of security in a crypto system as when quantum computers become widely available, or at least available and reliable. But a few hundred noisy qubits are not going to cut it. Okay, you will not be able to use a few hundred noisy qubits to break a state-of-the-art RSA-based crypto system. But people are worried, financial companies are worried, governments are worried. Why are they worried? Because coming down the line, in a few years from now, 5 years maybe, there are going to be quantum computers much more reliable than the current day technology, not because the qubits have become reliable, although they are also becoming more reliable, but because you'll have more and more qubits available for you, you can use a significant proportion of those qubits to do redundant computation or to do error correction. Okay, so that is, so you make the system fault tolerant through the introduction of redundancy. Not all the qubits are going to be used purely for computing purposes. The physical qubits are going to be noisy and unreliable, but within those physical qubits, you're going to carry out far more reliable and less noisy logical computation. Okay, so that's sort of this mapping between physical qubits and logical qubits, but it's going to be a very, overhead-heavy mapping. For every, sort of dozens of physical qubits may be mapped to a single logical qubit. So if you have a quantum algorithm that takes up, for example, Shor's algorithm to break like a 128-bit crypto system or 256-bit crypto system, you may require maybe dozens of logical qubits. Okay, maybe up to 20, let us say 20 to 50 logical qubits. But the scaling of that to physical qubits, noisy physical qubits, is going to be 10-fold or 100-fold. So you will need several hundreds to thousands of physical qubits, noisy physical qubits, to be able to realize even simple algorithms noiselessly in the logical level. All right, so but it is coming, and the promise is that it will come, and so governments are worried, and people are trying to move away from these more traditional crypto systems that are RSA based, which are based on integer factorization, into things that are supposed to be quantum safe. Okay. So there's a quantum computing roadmap that more or less every company these days carries around, but IBM publishes it every year, or like updates it every year. So they right now are in this horizon, we are in 2025. They say by 2033 plus, or at least within the next 10 years, they will see these massive quantum systems that can carry thousands of logical qubits. Okay, which can support thousands of logical qubits, not just thousands of physical qubits, thousands of logical qubits. That is the actual qubits that are going to be used for computation, which are going to be, physical qubits will be millions, okay, millions of physical qubits, but thousands of logical qubits. With that much compute power, you can do many things. You can do, then many problems actually become achievable. Many hard problems become achievable on a quantum computing system. But we don't know, so right now, things are on track. Whatever they've been saying up to 2024, 2025, more or less have been happening with maybe a lag of a year or two. So the things are pretty much on track according to this roadmap. So things are coming, so it is happening. But these big systems at the very end, these towards the end, it is where all of these use fault tolerance or quantum error correction techniques, okay, which are not there in the current systems. Current systems are simply noisy qubits, you do what you want with them, but the future systems are going to have inbuilt error correction inbuilt into them. So various quantum computing technologies are there, like superconducting qubits, photonics, bosonic computing, trapped ions, neutral atoms. All of them require their own customized error correction mechanisms, because the different systems, different technologies are going to be affected by different types of quantum errors. Yes, different types of noise is going to be different systems are going to be affected by different noise, because the physical systems are different, the physical noise are going to be different. Okay, so you have to try to figure out what that, characterize that noise, model it, and then build codes for that, or build error correction or fault tolerant schemes once you have a model for that noise. Okay, so it's all of these are ongoing efforts. Like, so any startup that, or any company that is in the business of developing a quantum computing system inherently also must like invest resources into quantum error correction, because that is, without a quantum error correction mechanism in place, you cannot build a quantum computing system at scale. So that is the motivation. So let me now quickly introduce to you how classical error correction works. We have been using error correcting codes or error correcting schemes in our daily lives without thinking about it. Your cell phones, your mobile phones will not work if they did not have powerful error correcting codes built into them. Extremely powerful codes. There's too much. Otherwise the wireless communication medium is extremely noisy. Okay, when you transmit a signal from here to some other, the other end of the world, that signal goes through a lot of, in between stuff. Even from here to the base station, the signal goes through a lot of attenuation, a lot of environmental noise, bounces off various, walls and other trees in between or walls in between, obstacles. All of this will cause attenuation. The signal will degrade. This is a base. So your whatever signal that you are transmitting from your phone, by the time it reaches the base station, it's very weak and it's highly degraded. It's very noisy. And similarly, the other way around, when the base station transmits a signal to you, it's the same thing. Signal is reaching you in a very degraded, it's a very noisy signal that gets to your phone. So that noise has to be beaten. You cannot ask for retransmission all the time, otherwise you will never have a conversation. Okay, you cannot keep saying, hello, what did you say, right? It's like you must have a real-time conversation, then you must have these kind of real-time error correction systems that are able to beat the noise. And that is what is going on, okay? That is what all your cell phones carry these, all your mobile phones or anything, any communication systems now will carry these powerful error correcting codes inbuilt into them. Okay, of course, these are classical bits. All the communication is classical. Whatever signals are there get converted into digital format, and in the digital format you introduce error correction. Okay. So here typically the model is like this, that you have a source that you have some messages coming from some source. It gets encoded, transmitted across a channel where noise gets added to it, then decoded, and that destination has to understand what the original message was. So the goal of this coding in here, encoder, is to reduce or eliminate the effects of channel noise. Okay, that is what is called channel coding or error correction coding. So you must have a certain model for the noise. Usually we take a randomized probabilistic model for the noise. So different error events in the channel occur with different probabilities, and you have an understanding of that through some channel characterization. So a typical example is where you're in the channel, when you're transmitting bits may get flipped. A 0 may become a 1 or a 1 may become a 0 with some probability, and every bit gets flipped independently of other bits. Okay. So in this case, like if you have an encoder could do the following. It takes a single bit and repeats it 3 times before it transmits it across the channel. That's an example of a channel code. Okay. A single bit of information or bit of data is being repeated 3 times before. So what is being transmitted across the channel are 3 bits. For every message bit, 3 coded bits are being transmitted across the channel. Now if one of them were to get flipped in transmission, you still have 2 correct bits. The majority is still correct, and the decoder will know. The decoder algorithm is simply majority logic. If majority is telling me it is what is sent, if majority being received is 0 as opposed to a 1, then you decode as a 0. Then you take the message to have been 0. If majority is a 1, you take the message to be 1. Okay, this will work when there is a single error in the system, and when the channel makes only a single error. If it makes multiple errors, of course you're out of luck. But then what else? We don't have miracles occurring here. If you could already, if there was telepathy that you could always use between the transmitter and the decoder and the receiver, then there is no need to have any physical systems at all that are being used for transmission. Okay, then you will always know what the transmitter is telling you to do, what the transmitter is trying to transmit. So in the absence of telepathy, you need these systems, and these systems are of course only physical systems. They will only work up to a point, up to what the system is designed for. When errors occur beyond the capability of the system to handle, the system will also fail. Okay. All right. So this code can correct single errors. Any single error occurring in transmission in one of the 3 bits will get corrected, because the decoder will simply flip that bit back and say that what was transmitted was these 3 bits. Okay. A more complicated coding scheme was discovered by Richard Hamming. So this coding scheme, the previous coding scheme, has rate 1/3. one message bit per 3 coded bits. Okay, so ideally you don't want to add too much redundancy in the system, because like that will take up, the more redundancy you add into the system, adds more delay in your decoding. Your decoding delays get like if you're investing a lot of resources into just error correction, if you're not utilizing the system efficiently, you're not utilizing the channel efficiently, and it's also finally the algorithms that you're using on your phone also have to take whatever is coming in, the entire bits that are coming in, it has to process them. If you have a large number of bits being used simply for error correction, the processing will take up time, okay, and of course also resources. So you want to keep the extra redundancy to a minimum. So you want to keep this rate high, number of message bits per coded bit you want to be keeping high. 1/3 is not great. Okay, so there's a scheme that, for example, was discovered by Richard Hamming in 1950-ish, which takes in 4 message bits and produces 7 coded bits, which is also capable of correcting a single error in transmission. Okay, so this is a rate 4/7 scheme, better than half now. Okay, whereas the previous one was rate 1/3. How does this scheme work? It takes 4 information bits and appends 3 extra bits to the end, called parity bits. Okay, and the way it does it is a very clever scheme. It draws a Venn diagram like this: blue circle, red circle, green circle. Puts the 4 message bits into the intersection regions of that Venn diagram. Okay, and the 3 parity bits in the regions of the Venn diagram belonging to a unique circle. The only rule now is that you have to choose your parity bits P1, P2, P3, given U1, U2, U3, U4. Those are your message which you don't have control over. Somebody is giving you the message to transmit. You have control over what parity bits to add to that message. You choose your parity bits in such a way that every circle contains an even number of ones. Okay, the messages are only zeros and ones. So if you have, for example, here, so the first circle contains these bits P1, U1, U2, and U4. U1, U2, and U4 are given to you by the message. You can choose P1 so that overall you have an even number of ones. Okay. Similarly for P2 and P3. Okay, so each circle should have an even number of ones. So just to give you an example. So if I look at this here, so the 4 message bits were 1, 0, 0, 0. Then to add a parity bit, what should P1 be? Someone speak up. 1, right? Because that will make it an even number of 1 in the blue circle. In the red circle, what should P2 be? Okay, and then the green circle, 0. Okay, and that's it. All right, so this is, and so what gets transmitted is those 4 message bits followed by these 3 parity bits. The claim is that this is capable of correcting a single error. If one of these bits, no matter message or parity, were to get flipped in transmission, you will always know which bit got flipped in transmission. The decoder will always know which was the bit that got flipped in transmission, provided that exactly 1 bit got flipped. If more than 1 bit got flipped, the decoder will get confused. So this again is only capable of handling a single error, okay, in transmission. So for example, so here what is happening is that the second bit got flipped in transmission. Okay, so this code word was transmitted, but in transmission the second 0 became a 1. Okay, the second bit got flipped in transmission. So you set up the same Venn diagram. Okay, with this in the same positions as before, you set up that same Venn diagram with what you have received, with the noisy stuff. Okay, so now these the data positions carry 1, 0, 1, 0. The parity positions are the same as before. Of course, the decoder does not know which are the correct bits or which are the wrong bits. The decoder's job is to figure out which are the correct bits and the wrong bits. The algorithm is known to everybody. Which are the message bits, which are the parity bits, everybody understands. Okay, so now what the algorithm does, see, the assumption is that a single bit went wrong in transmission. Only a single bit got flipped in transmission. If a single bit gets flipped in transmission, it will change the parity of only those circles to which that bit belongs. Obviously, right? Like it will change the parity of the circle, only those circles to which that bit belongs. So what you try to do is identify all the circles that have lost their parity, who have become odd parity here. Find the bit common to those circles only and flip that bit. That will obviously work. Then everything now gets back to being even parity. You found a single bit that when flipped back gives you everything having the right parity. That means that should have been a valid code word. So in this example, which is the bit that I should then, what will the algorithm try to do? So which are the circles that have lost their parity? Which colors? So green and the green and the blue circles have lost their parity. You look for the bit that belongs only to those circles. Okay, exactly to those two circles and not to the red circle. And that is this bit here. Okay, it belongs to the intersection of the green and blue circles but lies outside of the red circle. You flip that bit. Okay, you flip that bit. So this has been identified and you flip it. And yeah, I guess I've not put that slide here, but like you flip that bit and you will get everything being the same parity. Okay, so this is a very simple, this is a clever scheme that can perform single error correction, correct a single error in transmission. Multiple errors take place in transmission, this will fail because it is only looking to flip a single bit. It's only looking to flip one single bit. Okay, this algorithm is not even trying to figure out whether there are multiple bits flipped in transmission. Okay? It's always only trying to flip a single bit, a decoding algorithm. So it will fail if multiple errors take place in transmission. All right. So the point of these schemes is that by adding patterns to what you're trying to transmit, you can carry out some basic forward error correction without asking for feedback or retransmission. Again, this is used very commonly in communication systems. So the same principles we're going to carry forward and try to take it to quantum systems. Quantum communication we don't really communicate over quantum channels as of today, but we do computing over quantum systems. Computing systems are noisy. Okay, so qubits are noisy, and so to combat that computing noise that are being added to the qubits in computing systems, we build redundancy through the form of error correction, quantum error correction schemes. Some quick terminology because some of this could be useful a bit later. So we use, in classical error correction, we commonly use what are called binary linear codes. Okay, so that is a binary linear code in the language of linear algebra is a subspace of the space. So you have a field F2. F2 is the field of two elements, 0 and 1, under addition and multiplication modulo 2. Okay. You take all the vectors of length n over F2, binary vectors of length n. You consider some subset of it which is closed under addition, that are coordinate-wise addition. That is, take a subset which having the property that if I add any two vectors in that subset, I get a third vector also in that same subset. Okay, that is basically a subgroup, or in this case, what is called a subspace. Okay, such a code is called a linear code because it is closed under taking linear under addition, because it's a binary system. It is supposed to be closed under taking linear combinations, but the only valid scalars that you can use in linear combinations are zeros and ones because all the system is binary. So linear combinations effectively just means adding two things. Okay, so taking a linear combination of two vectors is the same as adding two vectors. So it has to be closed under the addition of two vectors. So this forms a subspace. When I consider a subset like that, it forms a subspace, and the dimension of that subspace is called the dimension of that block of that linear code. So you have, and that is the number of message bits that the linear code can carry. Okay, the message bits the linear code can carry is equal to the dimension of the linear code, and the number of the block length, how many coordinates are there in that vector space, that is equal to the number of the bits that are being used for transmission. Okay, physical bits and the message bits are the logical bits. That is the way that we think about it also here. Okay, so the dimension of the linear code is the number of logical bits, that's the number of data bits, and the block length of the linear code, so how many bits are there in the vector space, how many coordinates are there, n, that is called that is the number of physical bits that are going to be actually used for transmission. Okay, so you have logical bits get encoded into physical bits and transmitted. Okay. So an n comma k linear code has n physical bits, k logical bits. Okay. So to specify linear codes, we usually operate with generator and parity check matrices. So because it's a vector space, because a linear code is a vector space, it must have a basis. It has a vector space of dimension k, so it must have a basis with k vectors, k linearly independent vectors. You choose those basis vectors and stick them into the rows of a matrix. Such a matrix is called a generator matrix because the row space of that generator matrix is equal to the code that you want. Okay, the code is equal to the row space of this matrix because it is taking all linear combinations of basis vectors. Another way of viewing a code is as the null space or the kernel of some other matrix. Okay, every vector space is orthogonal to another vector space. So take a basis for the orthogonal vector space, stick that into the rows of the matrix, and that is called a parity check matrix. Okay, because the code words or the vectors that belong to the code lie in the null space of that matrix, null space of the parity check matrix. So parity check matrix basically tell you, sort of, they take particular bit positions and tell you that these must sum to 0. These are the parities. Okay, I want to add parities in such a way that when I add up certain positions from in my code word, I should get 0. That means that those positions must carry an even number of ones, because all operations are done modulo 2. So even is equal to 0, odd is equal to 1. Okay, when I take certain positions in my code word, they must carry an even number of ones. Okay, and the parity check matrices tell you which positions must carry an even number of ones. Okay. All right. Okay, so let me skip beyond this. Now let us go to quantum error correction basics. So as in the case of the classical code, we have logical bits and we have physical bits. Logical bits are the message carrying bits. You could have some way of mapping message bits into the n physical bits, that is called an encoder, or some physical the mapping that encodes message bits into coded bits, like repeated 3 times or use the Hamming mapping. Those are mappings that take 4 bits into 7 bits or 1 bit into 3 bits. Okay? So the k logical bits are mapped into n physical bits into one-to-one fashion. Okay? That is called an encoder mapping. Typically it's a linear map. Here as well we have such a mapping. Okay? There will be k logical qubits getting mapped into n physical qubits. So firstly, what is a qubit? I mean, hopefully that has already been explained to you in other parts of this program. A qubit is, as opposed to a bit only lives in 2 states, a 0 state or a 1 state. Those are the only 2 possibilities for a bit. A qubit lives in a 2-dimensional vector space. It has 2 basis vectors, one of which I will call ket0, or the other one calls a ket1. Okay, so ket0 and ket1 are 2 basis vectors. It's a 2-dimensional vector space, so this ket0 and ket1 are 2 basis vectors. You can think of them as being the vectors 1, 0 and 0, 1, standard basis. Okay, but there are 2 basis vectors for that 2-dimensional subspace. They are orthogonal. These are 2 orthogonal basis vectors for that 2-dimensional vector space. It's a complex vector space now. So meaning that, like, when I take linear combinations, I'm allowed to put vectors can have complex numbers inside them, and you can allow, when you take linear combinations, you're allowed to take the scalars to be from the complex field, from complex numbers. Okay, so these scalars alpha and beta here, when I'm taking a linear combination of ket0 and ket1, the scalars alpha and beta are complex numbers. Okay, so every vector, every qubit, any qubit is a vector lying in that, is a 2-dimensional vector. Okay, any qubit is a 2-dimensional vector. It can be expressed it can be uniquely expressed as a linear combination of the basis vectors, of the basis vector ket0 and the basis vector ket1. There is one additional property that a qubit requires, is that it should be normalized to have length 1. Okay, so that means that these scalar coefficients alpha and beta should be such that mod alpha squared plus mod beta squared equal to 1, so that the length of that unit vector is 1. So every qubit is normalized to have length 1. Okay, this is by definition. So qubits are 2-dimensional vectors, complex vectors, normalized to have unit length. Okay. So we distinguish again, we draw a distinction between physical qubits and logical qubits. Physical qubits live in physical space. They are realized through some physical system. Okay, these are the physical objects like photons, electrons, atoms, that are actually states of which are going to be representing the states of the qubit. Okay, there's a physical system that is going to get some state of it, like some spin of the electron or spin of the photon or polarization of the photon, is going to represent the state of the qubit. Okay, so that's a physical realization. Even in bits we have to do this. We typically convert a bit into voltages. Okay, classical bits also, zeros and ones, abstractly we may think of them, but when they have to be put into a physical system, they have to be realized physically. They have some physical medium has to realize those bits, zeros and ones also. Okay, when we do transmission, we convert them into electrical signals, electromagnetic signals. Okay, so those electromagnetic waves are physical objects. The zeros and ones only remain in our minds. Numbers are things that we have constructed in our minds. the physical objects that carry these numbers, that represent these numbers, are physical realizations of these numbers. Same thing here. We have abstractions we have created of something called qubits. They must satisfy certain properties. But when you have to devise a computing system, we must realize these qubits in hardware. Okay, and so that hardware, like there has to be some hardware that realizes qubits in a way that satisfies the properties that a qubit is expected to have. So we use photons or electrons or atoms or whatnot, what have you, to realize these qubits. Those are the physical realizations, and these are what are called the physical qubits. Okay. Physical qubits, of course, by their very nature, being physical systems, are highly error prone. These are sort of at the these are at electron scales. So these are extremely error prone systems, very fickle systems. They are subject to quantum effects. They're highly prone to decoherence. You can prepare a system in a certain state, but it will quickly decoherent, when interaction with the environment will affect it very quickly and it will decohere from the state that you prepare it in. You can try to very carefully prepare a photon to take on a particular polarization, but as soon as you leave it to its own devices, it will start like wobbling around and behaving in all kinds of random ways. Okay? Within nanoseconds, that will start to happen. So these systems are just extremely fickle. You cannot leave them alone. You have to constantly keep prodding them to keep them in place. Okay? This is what I meant by physical noise. Okay? Logical qubits, on the other hand, are the abstractions in our heads. Okay? These are the systems upon which we develop these are the qubits on which we write our algorithms, on which we develop our algorithms. Okay? So we can code it up in software, but translate, it's like software. Okay? The logical qubits is like software. The physical qubits are like hardware. Software has to be translated into hardware. Okay, so that's how you have to think about like physical, logical qubits and physical qubits. Okay. So logical qubits are the software upon which a quantum algorithm is executed, whereas the physical qubits are the hardware upon which the system runs. You have to translate into hardware. So it's like when you write a Qiskit piece of code on Qiskit and ask for it to be run on the quantum hardware, there's a compiler at the back end that will carry out this translation. Compiling basically does this, any compiling when you write a code in C or Python or whatever, there is something that has to translate it into hardware so that the physical system can execute the computation. That process is called compilation. Okay, the same thing has to be done for a quantum computer also. Like you have to write your code for logical code that you write in software will have to get translated into physical hardware. Okay, that compilation process is going to take place at the back end. Okay. So you can have your algorithms so what we do is we create these clean algorithms which are which are in an ideal world, everything works without noise. You can develop very delicate superpositions and delicate measurements that you can have on your algorithms. But when you translate it into the real world, all of the delicacy gets lost because real world is not at all delicate, full of noise, full of objects trying to, full of just the environment is going to get in your way, get in the way of the computation. So you must build in redundancy, you must build in fault tolerance schemes that can actually, when faults do take place in the physical hardware, there should be a means of overcoming them. Okay, there should be a way of getting over these faults. Okay, so there is a mapping, when you do this mapping from logical qubits into physical qubits, just like in the classical setting, when you do mapping from logical bits into physical bits, some of that parts of that mapping are being used purely for error correction purposes. Same thing we will be doing here. So parts of this mapping are going to be used purely for error correction. So you'll have very few logical qubits being mapped into large numbers of physical qubits because the noise is just very hard to defeat. Okay, so you have to use a large number of physical qubits to just carry a small number of logical qubits. Logical qubits, we want to keep as clean as possible because we want to execute our algorithm on them. The physical qubits, will be subject to heavy noise. Okay, and this mapping between logical to physical, how many physical qubits you require for a logical qubit will depend on the noise that you have to encounter in the physical system. Okay. So dozens is really an underestimate. It's really hundreds. Order of hundreds of physical qubits are required to carry a single logical qubits in current state, in current systems, where things currently are. Okay. Gates are ways of manipulating, just like in the case of digital computation, digital logic, you have gates, XOR, ANDs and ORs and XORs and NOT gates. You must have also ways of manipulating qubits. So qubits are manipulated using quantum gates, and quantum gates by definition or by nature, by physical nature, are supposed to be linear operations. Only linear operations are possible on qubits. Qubits are vectors, remember. Okay, living in some vector space. Only operations on these vectors that are allowed are linear operations. Okay, that is the nature of that is how nature works. Okay, the Schrodinger equation is a linear equation. Okay, so the way when you evolve a system, quantum system, a physical system, it evolves according to a Schrodinger equation. So the evolution, you initialize the system in some state, and evolution will take you to some final state. In between is a linear process, from initial state to final state. So a linear process, that linear system is modeled as a matrix, as a gate, as a unit. It has to be a unitary matrix because you want to preserve the length at both the ends. It's a qubit. A qubit has to have unit length. So to be able to preserve length after after a gate has been affected on the qubit, so that the output is also a qubit, the linear operation in between has to be unitary operation. Unitary operation preserves lengths. Okay. So quantum gates are unitary operators. Okay, and so this is what a unitary matrix is. It has the property that U dagger U is equal to identity. Okay. U dagger is a complex conjugate of U. So U is an n by n matrix. U dagger is its complex conjugate, and U dagger U should be equal to U dagger should be equal to the identity. That's called a unitary operator. It has the property that it preserves lengths. Okay, when it acts upon a vector of a certain length, the output will have the same length. In fact, it preserves angles. Okay, if I take two vectors and let the same operator act upon both these vectors, it's just like a rotation. It will keep the angle between the vectors the same. Okay, that's what unitary operators do. These are again linear operators, so it suffices to define their operation on basis vectors, and everything else then is defined through linearity. Okay, because all you have to know is what the operator does on basis vectors, on the ket0 and the ket1 vector, and thereafter everything else, any other state. So these states like in between that like are in linear combination of zeros and of ket0 and ket1 are said to be in superposition. Okay, it's a superposition of ket0 and ket1. So any vector in superposition, so if I define the linear operation on the basis vectors, then any vector in superposition of the basis vectors, the linear operation gets automatically defined on the superposition also because the operation is linear. Okay, so that when I take alpha times ket0 plus beta times ket1, what you will get at the output is alpha times u of ket0 plus beta times u of ket1 by linearity. Okay. So quantum gates are linear operators, and they are unitary operators. These are important things. Because they are unitary, they are reversible. Inverse exists. So, that is as opposed to in classical systems, in digital logic, you can take, for example, an XOR gate. XOR takes 2 bits in, 1 bit out. It is not reversible. Okay, 2 bits in and 1 bit out is not a reversible operation. Quantum bits inherently are reversible. Quantum gates inherently are reversible because these are invertible matrices. It will take the same number of qubits in and same number of qubits out. Okay. And it will also be reversible. That like if I feed it in the reverse direction, that is like if I look at, I can reverse it. I can reverse the quantum gate by applying the dagger, the inverse of that gate. Okay. Some basic quantum gates that we invariably study are the bit flip gate or the X gate, which acts like the standard flip gate, like the standard NOT gate in digital logic, except it's a quantum gate. So on the basis vectors, it acts like a NOT. On ket0, it makes ket0 into ket1 and ket1 into ket0. And everything else, it like acts by linearity. Okay, so alpha times ket0 plus beta times ket1 will become alpha times ket1 plus beta times ket0. Okay, so it is a quantum NOT gate. Okay, it's also called a bit flip gate. As a matrix, this is what it is doing. Okay, so this is the matrix. It takes the standard basis vectors 1 0 and 0 1, converts 1 0 into 0 1 and 0 1 into 1 0, and that matrix is the transformation corresponding to that conversion. There's another thing called the phase flip gate, which leaves the ket 0 vector unaffected, but flips the sign of the ket 1 vector. Okay. The ket 1 vector, because it's a vector, remember, so it is like, it could be a standard basis. In standard basis format, it will be 0, 1. It will take that 0, 1 and make it 0, -1. Okay, complex numbers, right? Like, so this is not digital logic, it is complex numbers. Okay, so Z of ket 1 is negative ket 1. So when you do superpositions, alpha times ket 0 plus beta times ket 1, you will get alpha times ket 0 minus beta times ket 1. Okay, this is called a phase flip gate. The relative phase between in this superposition is getting flipped. Okay. And this is the matrix corresponding to that phase flip operator. Another important gate is the so-called Hadamard gate. It is defined like this. It is that matrix. Again, its operation on ket 0 and ket 1 is like this. It takes ket 0 and makes it an equal superposition of ket 0 and ket 1. Okay, it basically gives 1 over root 2 weight to each of the vectors in the superposition. And the other one, the ket 1, gets taken to 1 over root 2 times ket 0 minus 1 over root 2 times ket 1. Okay. So that one, so the first vector we call ket plus, this vector we call ket minus. Okay, this is nomenclature, terminology. So that's another basis for the same complex vector space. Ket plus and ket minus form a different basis. You have standard basis and you have rotated basis. Okay, so this is just a different basis for the same complex vector space. So the Hadamard matrix basically is a basis change of basis operator. It takes standard basis, what do we call, in this terminology we call it a computational basis, ket 0 and ket 1, and converts it to a new basis of plus minus. It also has this like other interesting property that like it acts when you conjugate the bit flip gate with Hadamards, that is put Hadamards on either side of the bit flip gate, what you will get is a phase flip gate. And similarly, by the Hadamard is its own inverse, so I can just take it to the other side. Hadamards, if I take to the other side, apply it on the phase flip gate instead, I will get the bit flip gate. Okay, so Hadamards act upon, when I conjugate a bit flip gate with Hadamards, I get phase flip and vice versa. Another very important, so these are what are called the single qubit gates. Okay, these take 1 qubit as input and produce 1 qubit as output. You can have multiple qubits as input and multiple qubits, same number of, always you must have same number of qubits at the input and same number of qubits at the output, because these are invertible matrices, okay, in reversible gates. So you have 2 qubit gates. 2 qubit gates are a simple example, or the basic example, really the most important example, is the C0 gate, the controlled NOT gate. It is kind of, this is the most important thing because we need to have conditional logic in our algorithms, if-then kind of statements. These are the gates that are going to be used to execute if-then statements. If-then logic. Okay. So what it has are it has a control line and a target line. Okay, 2 qubits in, 2 qubits out. This is the gate in between. Okay, that is a 2 qubit, each line represents 1 qubit and that dot followed by the plus whatever sign. Entire thing is a gate. Okay, is a matrix. What it is doing is, it leaves the control line unaffected. Well, okay, first I will explain its operation on the computational basis, on ket 0 and ket 1. Okay, on the basis vectors ket 0 and ket 1, and then of course by linearity everything else also gets explained. So when both of these are in ket 0 and ket 1 form, it's called the control qubit. The control qubit does not get changed at all. Okay, when it is in the computational basis, the control qubit remains unaffected. The target qubit, this B qubit, may or may not get flipped. It will get flipped when the control qubit is a 1. When the control qubit is a 0, it does not get flipped. Okay. So effectively, so this is what is happening. See, the first qubit in these two, in this on the left hand side, the first qubits are the control qubits, the second qubits are the target qubits. Because the control qubits are 0, nothing is going to change. Okay, the target qubits are not going to get changed. So that is what 0, 0 stays as 0, 0, 0, 1 stays as 0, 1. Okay, when the control qubit becomes a 1, the target qubit gets flipped. Okay, so 1, 0 becomes 1, 1, 1, 1 becomes 1, 0. Okay, so 2 qubits in, 2 qubits out, and everything else through linearity. Superpositions of these 2 qubits will the action of this gate is through linearity. Is defined through linearity. Okay, this is very important for executing controlled operations, if then statements. If 0 then this, if 1 then this. You can have multiple qubit gates, like there's something called a Toffoli gate, where there are two control qubits and a single target qubits. When both the control qubits are 1, the target qubit gets flipped, otherwise nothing happens. Okay, that's called the Toffoli gate. It's also called the CC NOT gate sometimes, controlled NOT. It's a basic fact about quantum computing or quantum gates is that so we really only need single qubit gates and C NOTs to describe any unitary operation on qubits. Any multiple qubit gate can be realized through single qubit gates and C NOTs. The only 2 qubit gate you require are C NOTs. The single qubit gates you require a lot more. Arbitrary single qubit gates are required, not just X's, not just bit flip, phase flip, and Hadamard's, but something beyond that also. Arbitrary single qubit gates will be required for exactly realizing a multiple qubit gate. If you only want to approximately realize a multiple qubit gate, then you can also reduce the number of single qubit gates required. Okay, you can use just Hadamard's and one sort of a phase gate which introduces an irrational phase. Okay, something like that, whatever that means. So if relatively few number of gates are required to execute a quantum computer, any quantum operation, the basic gates, like in the case of digital logic, there's also a set of fundamental gates. Any digital logic circuit can be expressed in terms of certain gates. What are those gates? Okay, NAND. The NAND gate suffices. In fact, just the NAND gate suffices to execute any digital logic. Okay, that same sort of thing works here, but you need any arbitrary single qubit gate and the C NOT, or to execute quantum logic exactly. If you are okay with executing it approximately, whatever that means, then it suffices to just introduce some rotation gate, one specific rotation gate, and the C NOT and the Hadamard. Okay, so that is one. That's a result. That's a theorem. Okay, now I'm in the position to describe errors. So we will typically deal with qubits being in two types, being operated by simple errors. Bit flip errors or phase flip errors. Okay, the only kind of errors that we will currently worry about are bit flip errors and phase flip errors. As we will see, this suffices. Because it turns out that like these basic errors can be used to describe any arbitrary error as well. Any arbitrary error can be written in terms of just these basic errors, can be expressed just in terms of these basic errors. When I say arbitrary error, an arbitrary single qubit gate acting upon a single qubit can be expressed in terms of just bit flips and phase flips. Okay, we will see how that is done. Okay, so bit flip error is exactly that, the action of the X gate, the quantum NOT gate. The phase flip error is the action of the quantum phase gate. Okay, the phase gate, the Z gate, the phase flip gate. There is one very important theorem that kind of acts as an obstacle to quantum error correction. One of the basic schemes that we saw in classical error correction is the so-called repetition scheme, where you repeat any bit that you would like to transmit reliably, just repeat it enough number of times so that some parts of the transmission will go through without error. That's called a repetition code. That means that you're able to clone or copy a bit arbitrarily as often as you want. An unknown bit at the input can be copied as often as you want. We are very good at copying classical bits. We may not know what see, this is different from preparing. Copying, the action of copying is different from preparing a bit in that particular state. Copying just takes some, it is a map, create some, copying is this action. That is, you have some unknown bit at the input, some operation that will take this unknown bit and create a new copy of it. Preparation is where you take this unknown bit, okay, I want to create a new bit precisely the same as this unknown bit. However I used to prepare this first bit, I will use the same action to prepare the second bit. That is not called copying, it is called preparation. Okay. Copying is just take a bit, there is some blank slate I have available, I will take this bit and copy it onto that. That is a different operation than preparation. In quantum, you cannot do copying, you can only do state preparation. In quantum, copying is not allowed. Okay. In the quantum world, copying is not allowed because copying is not a linear operation. Okay, that is the basic problem. I can copy the individual basis states. Get 0 I can copy, get 1 I can copy. But if I have to take copy, then also a linear combination of it, it cannot be done linearly. Okay, and that is the basic problem. So in quantum you cannot do copying through the use of just quantum gates. So this is called the no cloning theorem. Okay, it's a major result that you cannot just copy. Whereas we're using copying as a kind of a fundamental way of doing error correction classically, that avenue of doing error correction in the quantum world is lost, is not available to us. Okay, that way of doing error correction is not available to us in quantum world. So for the longest time, for several, since quantum computing was proposed and quantum error correction was thought for quite a while that quantum error correction is actually not feasible. Because if copying is not feasible, if you don't know what your quantum state is, see, in the middle of your computation, if you have to protect your current quantum state, you can't go inside and see what it is. You cannot measure that quantum state because it kind of loses the properties that it is going to be used for computation. So it's some unknown state. If you have to protect it, you need some way of maybe copying it or something like that, unknown. I mean, you don't know what it is. I can't go look at it and create a copy of it, prepare a copy of it. It has to be done through some operation that will just take that and put it onto a blank slate. A new physical, some physical system that is currently in some random state, it will by some operation take this unknown qubit and map that unknown bit also into this same physical system. Okay, that kind of operation is not possible in a quantum computing system. So it was thought that if that is not possible, how can you do quantum error correction? How can you protect an unknown quantum state in the middle of computation? Turns out so then Peter Shor came along in the mid-90s and said found a quantum algorithm, error correcting scheme that actually works. It showed that it is actually possible to do quantum error correction without the ability to copy. All you need to be able to copy are the ket 0 and ket 1 states. The basis states, if you can copy the basis states, that suffices. Okay. So as a simple example of how quantum error correction can work, we'll take a look at the 3-qubit single bit flip correcting code, which takes one logical qubit, converts it into 3 physical qubits such that if any one of those 3 physical qubits were to be affected by a bit flip error, by an X gate, the effect of that error, you may not know which of those 3 qubits is affected by an error. Somehow, after the error has affected it, you do some measurement. So this is what you are doing here. You take a single logical qubit, you do some encoding of it, make it into 3 physical qubits. That single logical qubit along with 2 ancillars, because we are doing in quantum systems, gates have to take the same number of qubits in, same number of qubits out. Okay, so that logical qubit gets mapped onto some physical system along with 2 other zeros, systems prepared in some initial state, ket 0. Make some logic on it, quantum logic on it, you will get 3 output qubits, physical qubits. One of them gets flipped. Okay, flipped meaning X gate applies to one of them. You don't know which one. Somehow it has to be determined which one, and the effect of that X gate has to be reversed. Okay, this is called quantum error correction. Okay, this system allows you to do that. It takes this psi, that qubit there at the input, that logical qubit, need not just be ket 0 or ket 1, it can be in superposition of ket 0 and ket 1. But it is unknown. We don't know what it is. You don't need to know what it is. And this is the most important thing, okay, for quantum error correction. You don't need to know what the qubit is that you're trying to protect. You don't need to know what state it is in. Okay? So it is in some unknown state, but you do it, even if that you can, these two things you can prepare. Those two extra qubits that are adding, that are introducing into the system, you can prepare in that initial state ket 0. The gates you can do, you can use gates thereafter. You don't know what this is, but then you know, so you know now there are 3 physical qubits here. What the system says is that if one of those 3 physical qubits were to be affected by an X error, the effect of that X error can be reversed through some quantum logic. You don't know what that physical qubit is. You don't know what the logical qubit is, and you don't know where the error has taken place. All you know is that it is an X error, but I don't know which qubit is affected by it, which physical qubit is affected by it. Okay. So I can't observe, as opposed to in bits, I can observe the outputs. There are 3 bits at the output, I'll observe them. One of them now looks as different from the other 2, so I'll flip that one that looks different. But I can't observe it here. The process of observation, the rules of quantum mechanics, if I try to observe, if I try to measure, it will break the superposition, it will destroy the superposition. But I want to carry that delicate superposition in the middle of that quantum computation. I have to make sure that it remains as is. I should not be breaking it through measurement. I should not be destroying it through measurement. So all of this is geared towards keeping that superposition, that delicate superposition that has been created very carefully in your quantum computing system, keep it as is. I am not going to observe what it is. I will carry out some operations on it, gate operations on it. I might do some measurements, but it will not affect the actual the logical qubit psi in any way. Okay. This is the encoder. It takes that logical. So this encoder is just two C0 gates. The action of C0 is very simple. C0 simply does copying. Okay, so C0, when your initial gate, when the initial state of the target qubit is 0, all it is doing is copying the control qubit onto the target qubit. When the control qubit is 0, target qubit stays as 0. When the control qubit is 1, target qubit becomes 1. Okay, so that is the action of C0 is that. It takes the control qubit and copies it onto the target qubit, provided that the target qubit is initialized to 0, get 0. So of course I can always initialize the target qubit to get 0, no problem. Now, if it is a superposition, if the control qubit is in a superposition of 0 and 1, what you will get at the target qubit is a superposition of 0, 0 and 1, 1. Okay, because 0 becomes 0, 0, 1 becomes 1, 1. Okay, so what will then happen, so not at the target level, the 2 qubits, both the qubits together, see what was going on. Like here, we're in the C0 situation. Okay, in the C0 gate, control qubit, so target qubit is always 0. Okay, so this is 0, that is 0. Target qubit is 0. So the inputs are either 0, 0 or 1, 1. The outputs are then both become 0 or both become 1. Okay, depending on what the control qubit, if it is in ket 0, the output qubit stays in, then both the output qubits are in ket 0. Control qubit is ket 1, both the output qubits become ket 1. If the control qubit is in a superposition of 0 and 1, the target qubit is initialized to 0, the output is going to be in a superposition of 0, 0 and 1, 1. Okay. Alright, so what this control qubit, so what this encoder is doing is simply taking ket 0 and making 2 copies of it, 0, 0, making it 0, 0, 0, ket 1 is being converted into 1, 1, 1. That's what those C0s are doing. And if the if that psi was in a superposition, then what happens at the end of that, like after these gates have been applied to it, you will get a superposition of 3 ket 0s or 3 ket 1s. and 3 ket-1s. Okay, that is what you will have. You're not going to ever measure this directly. Okay, this is all as in some intermediate state of your quantum computation. But you're just applying these gates to that intermediate state of your quantum computation. So now if a particular error takes place, as I said, a single bit flip, if one of those 3 qubits gets flipped by an X gate, the effect is the following. So this is the errors, okay? No errors, I tensor I means no errors have taken place, identity acting on all the 3 qubits. X on the first qubit, nothing on the second 2 qubits, identity is on the last 2 qubits, or X on the second qubit or X on the third qubit, okay? Those are the possible errors that can take place inside this module E. The effect of that error is the following. So we know that the input, if there was no error, then the 3 qubit lines are carrying this superposition, if there is no error. If there is a single error, the first qubit is in error, then the first qubit is getting flipped in that superposition. Okay, so what the 3 lines will then be carrying after that error has taken place will be these 3, will be this superposition. If the second bit were to be in error, then the 3 lines will be carrying this superposition. If the third qubit were to be in error, then the 3 qubit lines will be carrying the third superposition, the last superposition, the fourth of them. Okay, so all right. So, but we don't want to. Since we don't want to do a measurement to know, I mean, if we try to measure what is going on at the output, you will destroy the superposition. Okay, we don't want to do that. Okay, we want to keep that psi as much as possible. We want to retain the superposition that psi is in without changing it. Okay. So what we do instead is introduce some extra what are called syndrome qubits, some more extra ancillary qubits that will be used to diagnose the error. What type of errors have taken place? Some diagnosis of that error will take place through the use of extra syndrome qubits. These are like our parity checks. Okay. So what this first syndrome qubit, the way it has been set up is that it is going to take the bitwise sum of the first qubit line and the third qubit line. That is what this syndrome qubit here is doing, taking the bitwise sum of the first qubit line and the third qubit. In other words, if what is on, so for example here, if what is being carried in these 3 lines is this superposition, what is going to be computed as the first syndrome qubit is going to be the sum of the first 1 here and the last 0 there, and the first 0 here and the last 1. That is like you will get alpha times 100 followed by on this. So there are 2 extra lines being added to it. Okay, there are 2 extra qubits being added to this computation. I am going to append those 2 extra qubits at the end. The first qubit is simply taking the bitwise sum of the first line and the third line. The second qubit is taking the bitwise sum of the second line and the third line. So the 2 extra qubits are going to be added. If you look at what is happening here, if I add the first and the third, or either here or here, I will get a 0. If I add the second and the third, either here or here, I get still a 0. So no matter which of these, in any time I take whatever it is, whatever the actual state here may be, whatever superposition alpha beta, I don't need to know what alpha and beta are, because the result is invariably going to be 0, 0 only, if those 3 qubit lines were in that superposition. If they were in this superposition instead, I will get a result of 1, 0 in my syndrome lines. If it was in this superposition, I will get a result of 0, 1. If it was in this superposition, I will get a result of 1, 1. See, this is able to now, these syndromes are able to distinguish between what type of errors take place without destroying the superposition itself. Okay, it is able to tell you by measuring the syndrome, I can now tell which of those errors have taken place without doing anything to this part here. That is not getting affected at all. That measurement is not destroying the superposition there. Okay, and this is what allows for error correction to take place. So once I do measurement, so compute the syndrome, measure the syndrome, so I do measurements here, If I measure the syndrome, I will know what the syndrome bits are. That will tell me what errors have taken place, and I'll just reverse the effect of those errors. Once I know what the errors are, those are just gates. I can just put those, it will tell you that the second qubit is an error, X error has occurred in the second qubit. Okay, put an X on the second qubit line and reverse the effect of that error. So this is how you do quantum error correction. In a very, very simple setting, when you know that a single X error has taken place. Okay. The same idea now can be extended to correct instead of a single X error. If my system is such that I have to correct a single Z error, essentially the same idea works by converting X errors to Z errors through the use of Hadamards. Remember, conjugation by Hadamards allows you to convert X's to Z's. That's what we do. If I know that inside here some Z error has taken place, I put Hadamards around the error, around the channel. One at the encoder end, one at the decoder end. Okay, then effectively the channel is putting these Hadamards around the channel, around where the error has taken place, converts that Z error into an X error. And I know how to convert X, I know how to correct X errors already. Okay, so this is a mechanism for converting Z errors into X errors, and we know how to correct for X errors. This is a very classical way of doing. We know to solve a particular problem, given a new problem, try to map onto the original problem that we know already how to solve, and solve that. This is a mapping from the new problem to the original problem, that for which we found a solution. Okay. All right, so converting X errors to Z errors. All right, now, so effectively the encoder here is this. Okay, so the encoder is the same encoder as before, except now we have further Hadamards being added to the encoder end. Okay, so what now with the encoding is, if that psi were in the ket 0 state, it is going to get up. Before the Hadamards, you have 3 zeros. After the Hadamards, you have 3 pluses, because the Hadamards convert the zeros to pluses. Okay. Similarly, the one before the Hadamards, the 3 qubit lines are in 1, 1, 1 state. After the Hadamards, they become in the minus, minus, minus state. So the encoder converts ket 0 into 3 pluses, ket 1 into 3 minuses. These are the logical 0 and logical 1. Okay, and superpositions are superpositions of these 3 pluses and 3 minuses. Okay, so the previous code, the bit flip correcting code, was converting ket 0 into 3 ket 0s and ket 1 into 3 ket 1s. Okay. In the previous case, the single bit flip code was converting a ket 0 into 3 ket 0s and a ket 1 into 3 ket 1s, and everything else through superposition. Here, ket 0 is converted into 3 ket pluses, ket 1 is converted into 3 ket minuses. Okay. But this allows for phase error correction as opposed to bit error correction. Okay, but these are very, very specialized codes. You'll never encounter noise which is only bit error or phase error in practice. Noise is going to be arbitrary quantum noise. So how do you deal with that? Shor's idea was to combine these two codes, the phase error correcting code with the bit flip error correcting code. The idea is something called concatenation. You take your original qubit, logical qubit, 0, first encode it using the phase error correcting code. You create 3 pluses from that single 0. Or from the 1, you create 3 minuses, and superpositions, of course, will go through as superpositions. Each of these pluses will now further get encoded using a bit error correcting code. The bit error correcting codes convert zeros to 0, 0, 0, 1 to 1, 1, 1. These are pluses. It doesn't take a plus and make it plus, plus, plus. What it will do, well, a plus you have to first express in terms of 0 and 1. Plus is a superposition of 0 and 1. A plus is this. So when the bit error correcting code is applied to plus, encoder for the bit error correcting code is applied to plus, it will act upon that plus through linearity. So it will act upon that 0, make it 3 zeros, act upon that 1, make it 3 ones, and like take that linear combination. That is what it will do at the end of plus. That's what plus will become. Okay. So that plus, so now what we are doing is taking 0, making it 3 pluses through phase flip code. Individual pluses are getting converted into this superposition of 3 zeros and 3 ones. Same thing at the minus level. These 3 minuses will get converted to this. So overall the code looks like this. So a single 0 gets converted to 3 copies of this state. And a single 1 gets converted to 3 copies of this state. Everything else is through superposition. If the original bit is in superposition of ket 0 and ket 1, or if the logical qubit is in superposition of ket 0 and ket 1, the physical qubits, there are 9 physical qubits. Okay, because there are 9 physical qubits, meaning because the first guy converts the first logical qubit into 3 physical qubits, the second step converts each of these 3 physical qubits into further 3 physical qubits. So overall there are 9 physical qubits. Okay, so a single logical qubit is getting converted into 9 physical qubits. And this is the encoding. Okay, so a single logical qubit, 9 physical qubits, 3 here and 3 copies of 3. And this code turns out is capable of correcting an arbitrary unitary error. And absolutely any error can take place. You may not even know what error. Any unitary gate acting on one of those 9 qubit lines, physical qubit lines, can be diagnosed and corrected. Okay, this is a really powerful statement, and this is what makes quantum computing feasible. Okay, because you don't have control over the types of errors that can take place in your system, but you don't even need to know. You don't need to have that control. So I mean, I'm not going to particularly tell you, let me see, okay, so what I want to point out is that what this code will do, without going into the details, so what this code does, because like the way things are set up here, what this code can do natively is to correct a single bit flip error in each of those 3 physical qubits, okay, these copies. When I create these copies here, see, when I have these kind of copies like this, there's 3 copies of this. Within each copy of those, within each of those copies, I can correct a single bit flip error, because that's a single bit flip correcting code. Within each copy, I have a single bit flip correcting code. Okay, so within each copy, I can correct a single bit flip error. I can also correct a single phase flip error across copies. That is, if in these 3 copies, if one of those pluses became a minus, I can correct that through the phase flip correcting code. Okay, that is the capability of this code natively. This is the concatenation part. Natively, this is what it can do. Because it's a concatenation of phase flip with bit flip. Okay, that I don't want to explain precisely how it is in the interest of time, but it should not be too hard for you to believe that it can be done, because we have seen how to do phase flip correction. We have seen how to do bit flip correction. This thing combines phase flip with bit flip. So it's clear that this code being a bit flip correcting code, those 3 qubits being a bit flip correcting code, can correct a single bit flip error. So in each of those 3 bits, 3 copies of 3 bits, a single bit flip error can get corrected. Phase flip error, because there is a plus sitting here, plus sitting here, plus sitting here, or minus, minus, minus in each of these copies. If one of those pluses were to become a minus and one of those minus were to become a plus, that can also be corrected. Okay, so that is called single. So this can be corrected natively. It turns out that this suffices to correct any arbitrary error as well. So what then it can also do, on top of correcting bit flip and phase flip errors like that, it can then correct a single XZ error. XZ meaning bit flip followed by phase flip on a single qubit. We don't know which qubit. Some qubit is affected by a bit flip and phase flip. That can also get corrected by first doing bit flip correction followed by phase flip correction. Okay, we do not need to know which bit. This is very important. We do not know which bit was affected by XZ, but you just run the decoder, first do the error correction for the, say, the bit flip error and followed by the phase flip error. Okay, and that decoder will automatically correct this combination of the bit flip and the phase flip error affecting a single qubit. Okay, that will happen. That just happens according to the way things have been set up here, this concatenation scheme. Now, and this is where the quantum magic really takes place, is that this then allows you to correct arbitrary unitary errors acting on a single qubit. So far, natively, we are only able to correct either single bit flip, single phase flip, or a combination of bit flip and phase flip. These seem to be pretty specific errors. I'm saying this can also, this is enough to do any arbitrary unitary error. You don't have to change your algorithm. You have to do something, you just have to do some extra measurement. And the idea there is the following. See, these matrices, the identity matrix, that means no error, X error, Z error, and the XZ error, together they form an orthonormal basis of the set of all unitary 2 by 2 matrices, all 2 by 2 matrices in fact. Okay, those 4 matrices, any other matrix, any other 2 by 2 matrix can be written as a linear combination of just those 4 matrices. This is a basic fact. Okay, this comes from linear algebra. Let me not explain why it comes. It's a linear algebraic fact. Okay, these are 4 linearly independent matrices, and that space is 4-dimensional. The space of 2 by 2 matrices is clearly a 4-dimensional vector space. There are 4 entries. There are 4 degrees of freedom. It's a 4-dimensional vector space. So you need 4 basis vectors for it, 4 basis matrices, and these are 4 basis matrices. And it turns out that so any 2 by 2 complex matrix can be expressed as this linear combination. And if this matrix A were to be unitary, then this linear combination has this extra property that the coefficients, the sum of the squares of these coefficients must be equal to 1. Okay, so for unitary gates, I can express them uniquely as a linear combination of I, X, Z, and XZ, where the coefficients of that linear combination have this property. Okay, they are normalized to have their sum of the squares to be equal to 1. All right. So now let us see what is now happening. So if a single unitary error were to be taking place in one of those 9 qubits were to be affected by a single unitary error, some u. We don't know what that u is, some u. Write that u can is expressible like this. We don't know what these coefficients alpha 1, alpha 2, alpha 3, alpha 4 are, because we don't know what u is. But we know that there is some alpha 1, alpha 2, alpha 3, alpha 4 having this property such that u is expressible like this. So then, by linearity, when this error, arbitrary unitary error affecting a single qubit, acts upon my 9 physical qubits, that becomes a linear combination of these types of errors. It's a superposition of an identity error, no error occurring on that logical qubit, on the 9 physical qubits, no error occurring, with coefficient alpha 1, a single X error occurring on the ith qubit with coefficient alpha 2, a single Z error occurring on the ith qubit with coefficient alpha 3, and a single XZ error occurring on the ith qubit with coefficient alpha 4. Okay, this is what it becomes by linearity. I don't need to know what that u is, but the effect of that u is this. It puts my state, the state of my quantum computing system, that error is now, the state of my quantum computing system is this. At this stage, measure. Okay, so now what we do is just, okay, so so what we now do is the following. We pass this entire system through the syndrome computation circuit. Okay, to be able, for error diagnosis, remember we were using syndromes. So we pass this entire error system, erroneous state, quantum state, through the syndrome diagnosis circuit. Everything being linear, it will again just attach itself, the syndromes get attached to the various parts of the superposition, the individual syndromes will get attached to the various parts of the superposition by linearity. Okay, so now the syndrome here, when there is no error, the syndrome is just all zeros. When there is a single X error, the syndrome corresponds to an X error on the ith qubit. When there is a single Z error, the syndrome corresponds to a Z error on the ith qubit. And when there is a single XZ error, the syndrome corresponds to an XZ error on the ith qubit. And these syndromes can all be distinguished from each other. So you measure the syndromes now. When you carry out a syndrome measurement, when you measure the syndrome, the outcome is going to be one of these four fellows. It will either tell you whether the outcome will tell you whether there was an X error on the ith qubit or a Z error on the ith qubit or an XZ error on the ith qubit. And not only that, the act of measurement breaks that superposition, but puts that state into one of the components of that superposition. We don't need to know which one either. It will put it into one. Then which one it will be given by the syndrome. The syndrome will tell you which one also. So once I know from the syndrome which state, which component of the superposition it has been put into, I can just reverse the effect, because now I know from the syndrome, I know whether it was an X error or a Z error or an XI Z error. Reverse the effect of that error, and I get back my psi L. The psi L I have I've kept unchanged throughout all of this process. I have not affected psi L at all. Okay, I don't even need to know what that psi L was. Okay, this is quantum error correction in its fullest, in full glory. Okay, this is how it works. Okay, so this illustrates the principle of discretization of errors. It suffices to correct X errors, Z errors, and XZ errors, combinations of bits and phase flips. After that, you can do things through superposition and measurement. Any other error can also be corrected. What time should I stop? Where is Bidhi? Done? Okay, so all right. So I just maybe say some few words. So there is an entire theory. So this gives you a basic illustration of the theory. There's an entire theory of quantum errors. Okay, that is quantum codes called quantum stabilizer codes. It's a big theory. I mean, I teach a course on this. There's a beautiful linear algebraic mechanism that the theory is based on that generalizes this idea of Shor's, the 9-qubit code. Okay, it can do very many powerful things. I will just leave it to say that. So in summary, what this error correction, how it works. You have an unknown state after error. Okay, so you have some unknown computing, some computation is taking place in your system. Your quantum computing system should be is in some unknown quantum state. Errors, it also has been affected by error. Okay, so that is the state psi here. That is the unknown physics. The actual computation should be in this state. After error, it has been taken to this state, psi dash. I want to get it back to being in the psi state. What one does is do syndrome measurements on the psi dash. Without affecting psi dash, one can carry out syndrome measurements. You determine the syndrome, okay, and then you basically by measuring this psi dash using certain observables, you determine a syndrome. Carry out a syndrome measurement. I mean, you determine syndrome by measuring the psi dash using some observables. Okay, these observables are called stabilizers for whatever reason. From the syndrome, you identify what the error operator was. Just like we have seen in the previous case, the syndrome will tell you whether it was X error, Z error, or XZ error. You identify what the error operator was and you correct it. Okay, so this is all that you have. That is how quantum error correction works in its most generality. Okay, it takes an erroneous state, a state with error, measures it using some observables to determine a syndrome. Those observables are designed in such a way that they should not affect that state psi dash. But it will get you some syndromes. Those syndromes you can use to diagnose the type of errors that have taken place. Once you know what errors have taken place, you just reverse the effect of those errors by applying the inverse gates. Okay, so that's where things are at, and so you have a large number of quantum codes developed over the years, many families of codes. So this is still a very burgeoning theory, lots of work still being done. In practice, these are deployed in practice. Topological codes, surface codes, you will see these LDPC, quantum LDPC codes. You will see this nomenclature in the literature. And here are some references for this talk. The quantum error correction zoo at the bottom is an excellent reference. It kind of compiles all the latest and greatest that is going on in this world. Okay. All right, with that I'll stop and take any questions if needed. Yeah.
So, sir, my question is, when you were explaining the syndrome measurement, so after the error occurred, just
Okay, somewhere here maybe?
for the 3 qubit, you were
3
explaining.
qubit, okay.
Yeah. So, so after that, you said that there is a bitwise sum. Because of that, like it changes. So how that bitwise sum is, like, I didn't understand.
Yeah, okay. I mean, of course, I don't expect you to understand, like, when I do this thing, so I have to get through a lot of material, so I can't do everything. So good, but let me sort of explain this. See, all of these are unitary gates. These are logical, these gates, so what is this gate? It's a 2 qubit gate. It is going to basically take that, because it has been initialized in this state psi, 0. See, if that original state was 0 already, what is this? The target state will carry, this line will then carry the same 0. 0 will get added to that 0 and keep it as 0. If that original qubit line was in the state 1, then this 0 gets flipped to a 1. So after that XOR is there, after that XOR you will get a 1.
Okay.
Then the same thing happening here. If this guy were to, if this guy were to be in 0, then it is not changing the bit that is at this point. Okay, when this guy is in 0, this is not changing the bit at that point. When this guy is in 1, this gets flipped to a 1. So effectively what is happening is, this 0 is getting converted to the binary sum of whatever qubits were on those two lines. If this qubit was both 0, 0, at the end of it you will get a 0. You see, these two qubits, those two qubits were both in 0, 0 state. The effect is, okay, the first guy will not get flipped, this guy will also not get flipped, the effect is still 0. For example, if one qubit was 1, the other qubit is 0. What is happening now? That 1 will flip this 0 to make it 1.
Okay.
That 1 will remain unchanged because the second target line is 0. So overall, this 0 has become a 1. That is the same as the bitwise sum of that 1 and the 0.
Okay.
If both were 1s, 0 will start becoming a 1 and then it will get back to being a 0.
So how these, like, after the, how do we know that exactly the initial state which is which after that error occurred, we will get the same exact state at the end of the thing?
Well, it is just, see, the syndromes have been chosen to make sure that you can diagnose the error. If one of these bits were to be different from the other two, the syndrome kind of tells you which bit. Okay, these are designed in such a way.
After we know that, okay, this bit is flipped, then we are doing something after that.
After that, it is just become, once you know what it is, see, this means if I see a syndrome like this, that means that this is the state that the system is in. If this is the state that the system is in, that means that the original state, which was this without error, got affected by an X error on the first qubit to make it this. So that means I know what the error is. I just put that first qubit back through an X gate.
Okay, understood. And it's just a reversible process which
It's a reversible process, yeah.
Okay, thank you, sir. Thank you, sir.
So there is a question. Why this error is termed as unitary? Is it always the case that error would be unitary?
Yeah, well, yes and no. So unitary is, there is, the answer is no, not necessarily. Error need not always be unitary. There are also things like, error is what is called a quantum operation. If the quantum operation is trace preserving, I think then the errors are unitary. If they are not trace preserving, in other words, you can have things like what is called amplitude damping. These are quantum operations which cannot be described just through unitary operators. But what is called polyerrors, polynoise, or decoherence, these are different. There are certain error mechanisms that can be described through unitary errors, but there are also other error mechanisms which cannot be described through unitary errors. You can approximate them through unitary errors, but they're not exactly, but they will not be exactly describable by unitary errors.
So error correction would work on those errors in somehow?
No, then you need different, you need different mechanisms to handle errors that cannot be described through unitary operators.
Sir, I have a question. So when we were talking about Shore's code, one logical bit got converted into 9 physical bits.
Correct.
So that means that if there are 3 logical bits, that would essentially get converted into 27 physical bits. And I mean, if we were to look at in a practical sense, that's a lot of processing power.
Well, exactly, sure.
So in the context of that, I wanted to ask you, where do you think we stand when it comes to having fault-tolerant computers in that sense? Because as you answered the previous questions as well, it's not just the unitary errors and the unitary operators that we need to take care. There are a lot more other things. So there are processing powers and maybe some undefined errors. So where do you think we exactly stand when we talk about getting a fault-tolerant quantum computer?
Well, I mean, you can't read all of this, but you can go to the IBM website and pull out the IBM quantum computing roadmap. It will tell you what they believe is the current state of the art. It's like right now we are somewhere here, okay, where, I can't read this here, but we are in the NISC era, okay, we are a few hundred physical qubits. And if you have 200 physical qubits, for example, and you try to use Shore's code, you will have 20 logical qubits. But that's a very useless code simply because it's only capable of correcting very simple single errors or something, very small number of errors. So, and you can't, 20 qubits, 20 logical qubits you can do a lot with, but the error mechanism that it is capable of defeating is kind of limited. If you want more, if you have to worry about a large number of errors, you need this mapping also you need much more powerful codes, much more redundancy also built into the system. So really the redundancy is of the order of 50 to 100 physical qubits to a single logical qubit. So for every logical qubit, you have to protect it with 50 physical qubits, let us say. Okay. So then if you have only about 500 qubits available, I can only have 10 logical qubits at best. Even that is really optimistic. So that is maybe where we are currently. Okay, we may have a quantum physical system of over 200 physical qubits kind of up and running. Maybe you can do 4 or 5 qubits of logical qubits of operation, not very much. But they say that by 2030 or so, you should have several hundreds of logical qubits available for clean logical operations. That means that you must have millions of physical qubits with error correction and fault tolerant schemes built into them, which allow you to execute algorithms on hundreds of logical qubits. So that is where things are.
Thank you, sir.
All right, okay, thank you.
Thank you, sir, for the wonderful talk. We'd now like to offer a token of appreciation on behalf of the organizing team. Please have it. So over the past 3 days, participants have worked through a series of problem challenges named Eigentrails, and we will soon be announcing the winners. A special note of appreciation to my fellow organizer friends. They barely slept while designing and testing those challenges to make sure everything ran smoothly. The hard work truly made this possible. Now, before announcing the winners, we are pleased to invite Professor Arindam Ghosh to deliver his talk. He'll give talk on importance of materials for quantum technologies and how to build a quantum ecosystem. where he shall present the necessity of some recent advances in the development of new materials and devices for quantum technologies. He shall show how new materials will impact all verticals of quantum technologies, that is, computing, communication, and sensing. Professor Arindam Ghosh is JRD Tata Chair Professor of Physics and the convener of the Quantum Technology Initiative at IISc Bangalore. He is an alumnus of the University of Cambridge and has been a visiting research fellow in nanotechnology at the T.J. Watson Research Center at IBM. Arindam co-created the vision document for India's National Quantum Mission and led design of the undergraduate quantum education for over 9,000 technical colleges and universities in India. He has received numerous prizes including the Shanti Swarup Bhatnagar Prize in 2012, the highest S&T Prize in India, and the Infosys Science Prize for Physical Sciences in 2020. He is also the co-founder and CEO of Quant2D Tech Private Limited, a deep tech startup developing commercializable devices for quantum sensing. So let's give a big round of applause for Professor Arindam Ghosh.
Yeah, that's not a problem. Hang on, there's something which it has to show. Yeah, at least it is connecting. Okay, thank you, Davarti. I think it's very nice to be here. We had very specific kind of lectures. I heard a little bit of Navin's talk, which is great. What I'm going to do is that I'm going to talk about a little bit of materials. I'm not really going to talk about the ecosystem. That's for a different forum. Over here, I would like to talk experimentalists. At the end of the day, hardware needs to be put in. So we need to find how to do that and where the bottlenecks lie. Which is why the materials and devices are among the most important areas. Almost any technology that you see today in the history of, human technology landscape has been led by new materials coming up, and silicon, then field effect transistors came out for germanium. So it had, if you look at even earlier, the thermionic tubes and all. So materials are essential not only to create technologies, but in this case, as quantum comes in, is it also about how to improve the technology. It's a continuous effort. Okay. Let me try. Is this the? I'll do this. Let's check it. It might be switched off. The battery might be a problem. Change it.
They have switched it off.
Okay, good. Works. So, as you all know, we had a beautiful lectures from Navin. So, the quantum computing is, of course, one of the key areas of quantum technologies, but it is certainly not the only one. As a result, there are three primary areas: quantum sensing, quantum communication, and I'm sure most of you here would already be aware of this diversity. And an ecosystem development must develop all three areas simultaneously. Okay. Quantum computing, you already know, you have the significant improvement over some of the applications and do certain things which is impossible to do with standard classical supercomputers today. Communication, of course, is for primarily secured communication purposes. You need a different set of equipments and devices, for example, single photon detectors and sources, among others, quantum random number generators. I might touch upon that. Quantum sensing promises something completely different. It actually gives you various types of sensors for some of the physical quantities like temperature, like electromagnetic fields, like magnetic fields, and even gravity. So they have completely different purposes. And as a result, the architecture for devices for the quantum sensing and the material requirement is also very different. Okay. So these are some blurbs which I already know. I don't want to spend too much time in this. So the first quantum revolution is just about 100 years ago, which is why this is the year of quantum. And we now are in a position to engineer our understanding over the last 100 years and make devices using these three areas, which beautifully said the entanglement, superposition, and measurements. And now there are devices with disruptive functionality, speed, and sensitivity. Okay. Now, I'm sure you all know this, but just a quick visualization of what superposition is. Superpositions are of two states, state vectors. You can either put them anywhere in the block sphere, and you can put them by using electromagnetic pulses. It's only when you measure that your system collapses into the state vectors, which is either up or down or 0 or 1, depends upon how you define it. And there are various ways in creating the block state and by applying appropriate potential. The difference is, though, the platform on which you achieve this is still not completely finalized. There are 5 key areas at this point of time. The superconducting one, which is IBM, has been working on quite heavily, but not just IBM, even Google and Rigetti. There's some companies which are already there. The photonic processor, semiconducting processor, trapped ion, and neutral atom. There are 5 key ones. There are additional platforms as well, which I'm going to talk about, just give you the information. Okay. Just a bit of history, and I like this one because it's very nice to talk to students and on this phenomenological and how the whole thing evolved over the last 100 years, essentially. If you have entangled qubits and you know what is entanglement as such, I like giving this sort of feeling, right? You send it one to Alice and another to Bob, and if Alice and Bob measure their qubits independently and essentially get a random output, and at the same time, to them they appear to be completely random because up-down two-state vectors. But if you take a look at them individually, and you see perfect correlation if the original qubits were entangled. Okay. And this was like as if the measurement of Alice on her qubit actually impacts the measurement of Bob, however far Bob is away. And this was a problem. And this is what Einstein, Podolsky, and Rosen didn't like. And in 1935 came up with a hidden variable theory, usually using information theory. But in 1964, Bell said that, okay, if there's quantum theory which is correct, which is entangled and action at a distance in some form, then the correlation bound is about 2.2. The experiment started after that in 1970s and 80s, and eventually got the Nobel Prize in 2022 by these 3 people, showing that actually the quantum theory was correct. Now, it's a race now, and it has become a race, worldwide race. And it's very rare to see a Nobel Prize given to 2 Nobel Prizes within 3 years going to the single field or a specific field which has been benefited by this work. So it actually shows the importance of how our technology landscape is moving, which is good. And even recently the announcement of Google on a specific advantage, quantum advantage, which just came out. Anyway, okay. So coming back to the platforms, which is where the materials and devices aspects are going to come in. And as I told you earlier, there are about 5 key platforms at this point of time. There are others, but those are at an earlier stage of development. Superconducting one is, of course, the one which is probably the most developed at this stage. It has certain advantages, high gate speeds and fidelities. And can leverage the standard lithographic processes. You can make them in a foundry here. But it requires cryogenics. You need a superconductor for that, right? Semiconducting one is an immediate competitor of that, and semiconductors are primarily those which are silicon-based. I'm going to come to that. It is completely compatible to the existing semiconducting foundry. Okay, you can make wonderful, extremely tiny quantum dots in a foundry and make qubits. Okay, the problem is that it also needs low temperature. There are companies on each, so that's the advantage. There are people who are betting on all 5 platforms. It's not like classical where the silicon is the winner by margin. Now the problem with semiconductors is that it is usually because the electrons in quantum dots interact with the host material very, very heavily. The coherence times are usually much lower than a superconducting system. We have the trapped ion ones. The trapped ion has extremely high gate fidelities at this point, but very long coherence time as well. The usual problems are very slow gate times in operations, okay? And the lasers, it's a very bulky system. You've got a large number of lasers around it. The neutral atoms, again, and finally the photonics one. The advantage of photonic one is that it is primarily a room temperature operation. So you have photonic circuits in which you make the electrons move around, the photons move around along waveguides, and you make computations at a room temperature circuit. However, that said, the detecting the photons are not always at room temperature. They require cryogenics. Okay, so this is by and large where the hardware platform for quantum technologies last. Okay, right now. So as you already know, hardware, in terms of hardware, what is a qubit? What you really are doing your error correction on is essentially a quantum two-state system which is kept inside a cavity. And you interrogate the quantum two-state system by shining an electromagnetic wave, usually in the gigahertz regime, and that gives you the state of the qubit you read out, right? So typically this is the Jaynes-Cummins Hamiltonian which does the job. This is the state of the two-state system, and this is essentially the coupling of the two-state system with external electromagnetic radiation, and you essentially look at this coupling which gives you you tune that and it gives you the frequencies and various other parameters. So now the way the engineering goes right now, you usually have an harmonic oscillator, particularly for superconductors. You need to remove the degeneracy. If you take a perfect simple harmonic oscillator, then the energy states are equispaced, but you do not want multiple states. You just need 2 states. So you use an anharmonic oscillator, okay? And that is why we create Josephson junctions. So this is a typical old age time, one of the first designs of a qubit, in which you have a cavity which is made of aluminium, which is superconducting, and you have the Josephson junctions in there. And what the Josephson junction does, it's as if it adds an L inductor, which is a nonlinear inductor, and that nonlinear inductor makes the energy spacings unequal, and you can use this and this as the qubit system. So that's the way the first hardware was created. Okay, typically you can see a 300 megahertz of anharmonicity with a distance between about 5 gigahertz. That's how the experiment occurs. Today, of course, it is different. For example, today, this is how a quantum circuit looks like, and you have at least 4 or 5 Josephson junctions with a lumped elements. These are inductors and capacitors as metal lines, which coupled to the individual qubits. You put that inside a dilution refrigerator. This is a dilution refrigerator, which goes down to about 550 to 100 millikelvin temperature. The electronic circuitry allows you to send electronic pulses or radio frequency pulses going all the way down here, and then look at the reflections and both manipulate and read the qubit state. Okay, so this is how the whole system works today. Okay, why do I need better qubits today? And how do I create better qubits is to first know what the problems with the qubits are. So one of the main problem of the qubits, the superconducting qubits, is the noise. Okay, how does the noise come in these qubits? Is that suppose you have an aluminum and an aluminum oxide junction, which makes a Josephson junction, which creates this anharmonic inductor. Aluminum oxide is an insulator, which is separating the 2 superconductors of aluminum. Now, in order to keep this region, you need to know exact current. You have to make sure the current through the junction to be same. But unfortunately, what happens, aluminum oxide is an amorphous superconductor region, and there are atoms or cluster of atoms that move around, and they lead to this kind of energy spacing, or essentially they couple to the superconducting state and creates noise. Okay, so instead of having your state vector exactly where you want in the Bloch sphere, it wanders around that, and that creates the noise. That's the noise that you want to avoid. So typically, if you look at it, this is the Hamiltonian, and you add a stochastic component to that. And if you look at the way the quantum information gets lost, you can do an integration over the autocorrelation function. And what happens in that, we see there is a noise which is 1 over f noise, okay, which diverges particularly at low frequencies, that degrades the T2 time and adds to the dephasing time. So this is something that from a material and device perspective, we need to avoid. Okay, so that's where many of the recent efforts have gone in, how to reduce noise, and I'll come to that. For example, one of the ways people have now found out a better material for qubits is no longer aluminium but tantalum. So you can use tantalum-based qubits rather than aluminium-based qubits, and that helps. Why? Because you see, tantalum is supposed to be much heavier than aluminium. So if I make a cluster of atoms using tantalum oxide, then those tantalum finds it very difficult to move around, and the noise is less, and that's why the current, the state vector remains roughly where it is. As a result, using tantalum now, we can increase the T2 time to approximately 0.3 millisecond without any problem. So it's actually getting better and better in terms of retaining the quantum information. Okay, so these are design criteria, and many of the new materials that are required for quantum technologies today in the computation area. Okay, this is just one example. There are examples in which what kind of substrate you require. Today it is sapphire substrate. How do you create better sapphire substrates, and so on and so forth. So the question that you ask, okay, I mean, I need probably about 1 million qubits. I'll come to that why million, that's a different question. But then is superconductivity is an answer to that question. But because the problem in superconducting qubit is that at the end of the day, what IBM is making today is that it's still very large. Of course, you can make a very, very large dilution refrigerator on a single if you take typically today from the largest dilution refrigerator, we can keep about 1,000 to 5,000 qubits. Roughly, you can stack them up in one dilution refrigerator. But if I want to have 1 million qubit, then I really need very, very large number of dilution refrigerators and communication protocols that connect one dilution refrigerator to the other. So that's a real problem. So the question that naturally was asked is, okay, can I shrink the qubits? And in superconducting architecture, it is very hard simply because you need to have this size in order to understand that the wavelengths of the RF is in that order. So a really fundamental limit in the size of the devices. So that's where the tunnel faults come in. The semiconducting qubit that Intel has made purely on the silicon germanium heterostructure. The advantage, as I said earlier, it is based on quantum dots. As a result, the whole thing is fixed on the fingertip. Okay, so very, very small, and integration possibilities are much easier. As I said, the problem is though that a very strong environmental coupling, and there is no coherent state like a superconductor state that protects the qubit. As a result, the coherence time is very short, and it's very hard to scale this up. Okay, the larger the qubit, the noise becomes much larger, the fidelity drops down drastically. So that's a material challenge in the semiconducting qubit side. So as a result, you can see that this is one of the groups in Australia that are really investing a lot in semiconducting qubits. And you can see one of the ways of creating these semiconducting qubits is by creating phosphorus atoms, really small phosphorus atoms, which are engraved in silicon environment. But these are essentially each electron, when they go through this from the source to the drain or the drain to the source, it leads to a peak in the current. This is the current or conductance in this as a function of a potential that you apply on this gate. Now the thing is that this is all fine, but the moment I try to put a gate from the top and put an oxide on this, you can see it's completely degraded. Okay, so this shows how strongly a semiconducting qubit couples to the environment, and you lose all the quantum features very, very quickly. So this is a big problem with semiconducting qubits. So Intel and Microsoft are looking into this, and they are having different strategies from here. For example, what Microsoft did recently, and this is still an open and debatable issue, that whether they can couple. The idea is very nice. The idea is to have a new type of particles called the Majorana modes, which happens at the junction between superconductor and semiconductor. Okay, or at least is predicted to happen, right? And we still don't have, I want to emphasize, we still do not have a clear experimental evidence of these Majorana modes yet. So these Majorana modes are expected to happen at the junction. So the advantage of this idea is that you have a way to protect the state against the environmental disturbances that destroy the semiconducting qubits. And so here we have a aluminum or indium antimony wire, which has got a strong spin orbit interaction, and which is coated with an aluminum one, and at the junction the Majorana modes are supposed to form, and these Majorana modes are expected to be robust against decoherence and other environmental fluctuations, significantly more than a standard semiconductor quantum dot. Okay, so as a goal, and the advantage of that goal is that you can now have the advantage of coherence of a superconductor, but you can integrate a very large number of qubits in a small space. Okay, so again, but the problem is we are still not sure whether there are Majorana modes there. So actually there are this work that is going on. And that led to at least a development of very interesting new materials. Materials that are superconductor-semiconductor hybrids. For example, an epitaxial growth of indium arsenide and aluminium on top of each other actually leads to a whole different type of material. So these are, you see inside the indium arsenide wire, and then the growth of aluminium around it. So you have actually a very different material that otherwise wouldn't have existed if the quantum computing was not being suggested in these systems. Another set of materials is this is essentially where we lie today. As far as the quantum landscape goes, there are 4 different type of materials. One is semiconductors, and there are silicon and germanium, germanium, and various other ones. There is novel superconductors are getting discovered, iron family, graphene, I'll come to that in a minute, niobium selenide, high temperature superconductors like bismuth, strontium, cobalt, copper oxide. Essentially, those are superconducting at 77 degrees, and you ask the question whether we can use those in various applications of computers. In addition to that, there are topological materials and two-dimensional materials. These are materials that are being continuously researched in the quantum technology front. Okay. To give you an example of what happens in two-dimensional materials, this has got graphene, which essentially these materials are layered materials in the sense that the atomic coordination is dense in a plane, but then there are large separations between 2 successive planes. Okay. Graphene is very interesting, and I'll tell you why. And there are certainly not graphene. There are several, about 30 to 40 materials today. Bismuth selenide, molybdenum disulfide, these are supposed to be semiconductors. And these semiconductors attract light very well, and you can use photonic processor and single photon detectors for quantum communication purposes for this. Graphene has a particular interest. If you take a look at graphene today, the typical layer-to-layer interaction is about 1,000 times smaller than a standard covalent on the ionic bond. So you can easily take out one layer and make a single atomic layer sitting on a plane today. Okay. The advantage is, if you take a standard semiconductor and device architecture, the electronic mobility of graphene is at least 100,000 times larger than the silicon device that you have in your computers today. okay, at room temperature. It can go to at least 1 million mobility, whereas a standard silicon processor that you have in your computer is about 100 to 200. So really, much larger mobility of graphene leads to much faster electronics, and it is not only interesting in terms, and I'll show you that in a minute, for quantum computing purposes, but also interesting from quantum peripheral purposes. You see, today we are all doing error corrections and great doing actual quantum computing, but at the end of the day, you need to read those data using classical electronics. You need to have a communication between the quantum hardware, which is at low temperature, and the classical hardware that is sitting at room temperature. And the peripheral design is as big a challenge today as making the quantum hardware, okay? So graphene and these new generation of semiconductors are not only interesting in terms of quantum hardware development, but also peripheral developments. So this is, for example, a semiconductor in molybdenum disulfide, because it has got a very different structure. It has got a band gap of about 1.9 electron volt, which leads to a very strong optical sensitivity. This led to a very large number of applications. In 2D domain, the semiconductor technology landscape, as you get smaller and smaller, you have not only quantum computing as an application, but also in spin-based memory devices and various other applications that are coming into play today. Let's talk about graphene once, and I'll tell you why graphene is an interesting, even in quantum hardware development. So one of the areas in which graphene is being used using bilayer graphene is to make double quantum dots, which are traditionally was being used for silicon germanium and the technology that is being used by Intel, okay? And they made the tunnel faults. So here, using graphene, the bilayer graphene in particular, this is a bilayer graphene where two graphene layers are sitting on top of each other within a distance of 3 nanometer, okay, 3 angstrom, right, 0.3 nanometer. What you can do is that by an assembly of gate, you can put in 2 quantum dots. These 2 quantum dots are like qubits. The electron can stay in one, or it can be a singlet and triplet combination. So it's very similar to a semiconductor quantum dot, but you can make it on graphene today. But what's the advantage? This is an actual device which have actually been done. The advantages are many. For example, graphene has got 2 types of thing to play with, 2 types of degrees of freedom. In a case of semiconductor quantum dot, it is singlet and triplet of spins. In graphene, there is an additional handle called valleys, in which the electrons can be in either spin or a valley degrees of freedom. Graphene electrons do not couple to the lattice very much, which is a key problem with silicon. So as a result, there are large spin relaxation time in graphene, which actually helps overcome certain problems in the case of semiconductors, okay? And you can naturally get isotopically pure carbon, which is very difficult to get in silicon. Getting silicon germanium, one of the reasons gallium arsenide was not being used is to get isotopically pure silicon. So there are various advantages, and there is steady progress. And this is, if you look at it, this is how the whole field has moved over the last 10 years or 15 years. 1990 onwards, it is the time taken till this to actually perfect the semiconducting platform, the silicon germanium. In the case of graphene, the whole process has occurred within last decade. So this is the speed at which a new material can actually change the hardware landscape very, very quickly. Okay. But if you tell this is something that's enough, that's not. There are some really exotic material platform on which quantum computing probably will happen. For example, electrons and helium. Liquid helium is a beautiful, clean, probably the cleanest environment an electron can be. And what happens is that because of the Coulomb interaction between the electrons, if you keep them on a surface of liquid helium, they self-organize and form a lattice. So this is a natural platform for quantum computing. A large number of qubits can be created. But the problem is that if you have an electron, how to read its state, how to read the spin. So a single electron ESR, or electron spin resonance, on liquid helium surface is the challenge, but it has now been solved in certain ways. So there's a company called EuroQ, which is now essentially investing in creating a quantum computer on a single electron, on electrons floating on the surface of liquid helium. It's really exotic, actually, if you think about it. In IISc also, Ambarish is working on this direction. By the way, how much time do I have? 5 more minutes? Okay, I'll finish in 5 minutes. Okay, so I gave examples of new material research and material platforms in the context of quantum computing, but many of these technologies are completely translatable to other areas. For example, in quantum communications, one of the key areas is where you need single photon source and a single photon detectors to make Bell state measurements. You require quantum random number generators in order to randomize the basis set in which the photons are being transmitted. Kaushik Majumdar is coming up with new ways of making these quantum random number generators with almost perfect entropy in terms of the true quantum number generator. Okay, for example, and that is used using quantum tunneling process. Quantum tunneling is quantum mechanically perfect random process. Okay, so if you can use, right now the usual random number generators are used from thermal noise, from various other sources, but getting true quantum number generator is a technological challenge, and new materials are being developed towards that. Okay. So for quantum sensing, I told you one of the key areas of quantum sensing is quantum magnetometry, and our goal is to make extremely high sensors that will go to extremely small dimension, very, very tiny space. And there are old techniques, like a Hall effect is a perfect way of, so Hall effect gives you large, very small sensors, but its sensitivity is not good. Bose-Einstein condensation is this, but they are very large. Spatial resolution is not good. For example, vapor cells are new areas which are in this type of, where you put in vapor of gas and you make them precise in external magnetic field. So they are very good, but really, I mean, this is where the current technology landscape is, in making high quality magnetic sensors. You may ask the question, why do I need magnetic sensors? Would you know how many areas a simple quantum magnetic sensor is going to become important? It's going to become important in MRI. So tomorrow, I don't want a magnetic sensing of my brain to be done by entering a big magnet. GPS denied navigation. So if I put magnetic sensors on my aircrafts, then I would like to see my aircraft use the Earth's magnetic field variation in order to go from one point to the other on the land. I don't need to communicate with GPS. So these are areas in which quantum sensing can actually revolutionize. It can be scary at some point because I will not be able to detect those aircrafts if they are not connected to the GPS. But at the end of the day, there are a lot of, every technology has a positive and negative. You can't do anything about it. Okay, so it looks like that in order to achieve this goal of having extremely high magnetic sensing at very short resolution, it is the new material that has come into play, and the nitrogen vacancies in boron nitride, vacancies in silicon carbide seems to be the solution that we would be looking for. And there is another area of materials. Okay, I'll just skip this. Okay, I will finish this talk with a little bit of overview of where we are and what a practical quantum computer will require. Where we would start worrying about things, and I have this last couple of slides, it's more of a general use. So what we have is what Navin just said about how to do error correction. So we have physical qubits, but we have to go to logical qubits, okay? And one of the benchmark, although it can be done at a, we can debate about it, but I would review a paper which was published in 2012, many years ago, by Martinez and Andrew Cleland and others. Essentially, what will be required at that technology time, at that time 2012-ish, how many physical qubits will be required to have a quantum computer that will actually do something bad or something interesting, which is essentially factorize. Okay, so the number is, say, in order to break the RSA protocol of say 2048, we need an order of 2000 qubit, and so that means it requires about 4000 logical qubits at that point of time. And if you use the Ansela qubits and various other things, you need at that time, because the quality of the qubits at that time was far weaker, far worse than what you have today. The error rate was about 10% below the threshold. We needed approximately 1 billion qubit. That was the estimate. About 1 billion qubit would have been required of that era to break the RSA protocol. Of course, that requires you apply 3 qubit gates and it run about, assume that each gate runs about 100 nanoseconds per operation. You need about 1 day to break RSA 2048 protocol. So that's the estimate that was given over there, okay? Now, let us look at the situation where we are today and where we are. So first of all, when do you think, if assuming RSA 2048 is still in place, which is not, which is being, the post-quantum cryptography is moving towards, but let's discuss and let's see where we are. So say the physical qubit count today, and what I have plotted here is the industry roadmap, with how the different qubits are different, this is superconducting one, how we improved over the years in the number of qubits that is available to us, okay, physical qubits. And this is the industry roadmap. Of course, we are here today. This is how the industry roadmap tells us. How the actual availability of the qubits happen is this dashed line. This is the number of qubits actually the industry made. So you see the industry actually made qubits which are improving according to the roadmap that they have created. It's not too far off, it is not completely off. Yeah? It's the number of qubits. It is just the number of qubits. I'm not saying whether this will make a useful quantum computer, it's just the number of qubits here. Okay. Now, how the algorithm aspects have changed in terms of the requirement of the available qubits to break the RS-2048 protocols. There has been significant improvement in terms of protocols, in terms of algorithms, right? So there are these, this was the 2012 paper which said that you need 1 billion qubit 10 to the 9 to break the RS-2048 protocol at that time. And then you see that things have improved, and then you see this paper in Quantum in 2021, that how to factor 2048-bit RS integers in 8 hours using 20 million noisy qubits. So I'm no longer sitting at 1 billion, I'm now at 20 million qubits, which is significantly smaller here. And there are now these new protocols are coming up, which is going to reduce the overhead of a physical to logical qubit to do the same thing much, much faster, much, much smaller. So this is something, assume that this is a, maybe Navin, you want to put one point here, and that might be of help. It will be a point somewhere here that how much resources required physical to logical qubit to do a job like this. Okay, that is break the RS-2048. Okay, so now you can see different hardware technology that is coming up. So you see at the end of the day, if I said trapped ion qubit, trapped ion logical qubit, so if you have a 10 physical qubit, then I reach about 1000 qubit. My goal is to have 1000 logical qubit to break that RS-2048 protocol. And with 1000 physical qubit on, say, superconductors to get 1 logical qubit, then I need to have at least 1 million physical qubits. Then I'm going to break the protocol. With a little bit of error mitigation, I can use 100 physical qubits to get 1 logical qubit. I will achieve that here. So typically, and if I use, say, trapped ion protocol with 10 physical qubit for a logical qubit, I actually do it here. I reach 1000 logical qubits somewhere here. So the range of possible dates over which the RSA protocol can be broken is actually anywhere from 2027 to 2035. So, okay, I mean, there are other issues, but this is an interesting analysis of the current quantum technology landscape. Okay, last slide, expectations, and we have to be grounded, we got to be realistic, we have to be practical. So this is the academia versus industry roadmap, and you need to see this. This is a paper which is which is on the archive. So please take a look at it. It's a beautiful paper. It actually says where the problems are and what kind of problems need to be sorted. In order to make a large number of physical qubits doesn't necessarily mean a large quantum computer. So there are material challenges in terms of reducing the crosstalks. There are material challenges when it comes to distributed quantum computation. So there are many, many aspects. So please read this paper. But hey, at the end of the day, this is where we are. Thank you very much. If you have any question, I can answer. Otherwise, we are done. Okay. I think we are done, Devati? Okay. Sure. Whatever you want me to do. Sure.
Thank you very much, sir, for the insightful talk on quantum hardware. Now, we would like to present a memento on behalf of our team.
Thank you.
Now, I would like to request Arindam sir to announce the winners of the Eigen Trails and congratulate them.
Sure. What do you want me to do? Just read out?
Yeah, Jatin and
Where do I read? These two?
Yeah.
Okay. I think first I would like to congratulate Jatin. Is he here? Oh, virtual? Okay. And second is Sachin.
Is there?
Okay. Congratulations, Sachin. Please give him a. Do you want to come up?
Yeah, please come.
Will he come up?
Yes.
Come.
Thank you. You will come over.
Get up. Take a picture. Okay. Congratulations. That's it?
Sir, will you please launch the hackathon for us?
Sure. What do you want me to do? So just
Say
announce?
few words, yeah.
Okay. So first of all, then it's my pleasure to launch the hackathon, which will happen today and tomorrow.
Yeah, from 3 p.m.
From 3 p.m. today. Okay. I think it's the hackathons are extremely important, and more I see it's happening at various levels. I was in a Swiss Quantum Summit just about 2 weeks ago, and there have been hackathons on. It's essentially a resource for ideas, and you got to take this seriously. The more you interact with each other, more you discuss, the more new ideas are going to emerge. And one of the aspects that really you should consider, and I'm sure you know about it, is how we can ensure quantum advantage. That's the most important aspect. We got to find out ways in which quantum advantage can be implemented and realized. So I hope your hackathon is extremely useful. You all enjoy your hackathon and make it productive. All the best.
So there's an announcement for the participants. The hackathon will start from 3 p.m. today and it will end on 3 p.m. tomorrow. So get set up for the hackathon and all the best. The prompts will be uploaded on the website, on the Discord itself. And I'd like to call up my organizer friends and the volunteers to the stage for a group photo. And the professors